Sure, yeah, and I was going to suggest that anyway. There shouldn't be anyone else at all coming by.
Is that door curved?
I know, it is, yeah.
It's cool. Amazing.
I think it's just part of the design. You know, a lot of these older houses are a bit like that. I mean, we used to stay in a flat in Shawlands in Glasgow. It wasn't that old, but it was a tenement flat from the early 1900s, and all the doors were different sizes. So we wanted to get new doors when we moved in, and we thought we could just go to B&Q and pick up off the shelf, but no chance. All different sizes.
No chance.
Yeah.
Great.
I think a lot of the Edinburgh ones are like that too.
Well, certainly these old houses, they'll be. It's not often you find a room this shape anyway, so it's.
I know, it's incredible.
It's absolutely gorgeous.
Make sure we get the right shots to show off. Show off the building.
Definitely will. Definitely will.
Of course, we've got a whiskey here for you.
Yeah.
I see you eagerly looking at it. We went for Macallan.
Sure.
For more than one reason. One, this is actually now quite a special bottle because it's been discontinued, so it's quite nice to try something that potentially could be the last time we try it for a while. I think it's still available,
right?
But they'll not be making any more of it.
If you see it, definitely worth picking a couple up because like I say, it's discontinued, so well worth having one. We'll do the honours.
Crack on.
Classic Speyside Dram.
Yeah, very much.
You can't get much more classic than Macallan.
Thank you.
No problem. It's great to have you, Martin.
Brilliant.
So we are rolling, Martin. So
yeah, we're
sure.
All the things you were saying off camera, don't worry. Don't worry, I've missed them out.
Grand. Thanks so much for joining us. Great to see you again.
You're welcome.
I appreciate you joining us, and I was just thinking about how we're going to start this off and the sort of vastness of this topic. We're here, obviously. It would be great, I suppose, if you could maybe just tell us a little bit about your expertise and
happy to, absolutely. Right? Yep, sure. Thanks. So, well, I'm from the West Coast, so I'm in somewhat uncharted territory here in Edinburgh. I'd like to say, welcome to my Edinburgh townhouse, but of course it isn't mine. We're here in 14 India Street in the Edinburgh New Town, which was the birthplace of James Clerk Maxwell, who's probably, in my view, Scotland's most famous ever scientist. But saying that, a lot of people haven't even heard of him at all. He's right up there with people like Albert Einstein and Isaac Newton in terms of the contributions he's made to our understanding of how the universe works. So I'm a trustee of the James Clerk Maxwell Foundation, and therefore seem to make good sense to come here. Absolutely. I don't know whether Maxwell was a fan of whiskey himself, but I certainly am. And while I've not achieved, his fame and level of recognition around the world among physicists, I am part of a global team of scientists that made a very significant discovery just a few years ago, what are called gravitational waves. So I'm Professor of Gravitational Astrophysics and Cosmology at Glasgow Uni. Quite a mouthful.
That I was just about to say.
Over the course of our discussion, hopefully we can unpack that a wee bit and tell a few whiskey tales along the way.
Absolutely, that's great. And in terms of James Clerk Maxwell, I mean, it is a great place to start. Probably we are here in this amazing, this gorgeous townhouse here in Edinburgh. I've never heard of him. I've heard of Einstein, I've heard of Newton. Why have I not heard of James Clerk Maxwell?
Well, firstly, he died when he was only 48, so in a way that didn't help. He was also quite a humble man. I mean, he achieved a great deal, but he lived at a time when there was no social media, there wasn't even really, photography. In fact, that's part of the story because he was one of the people that pioneered colour images and colour photography. We'll get to that in a bit. But all of that means that he was living, before the opportunities that we now have to put even scientists, in the spotlight. If you look at the last 2 years with the pandemic, there's a few scientists that have been very prominent, on our news every other day. Nothing like that for Maxwell in his time. Now, of course, Newton lived even longer ago. So you might say, well, why do we know about him? Well, maybe it's partly just because of the range of things that Newton studied and found out about, everything from gravity to rainbows and lots more along the way. The scope of Maxwell's work was also quite broad, but it was kind of deep. It was pretty full-on mathematical stuff, so not necessarily that easy to capture just, for a general audience, the way that some of Newton's stuff is, the apple falling in his head and stories like that. So I think that's all tied up with it. The fact that he was quite modest and shy, the fact that his stuff was quite kind of abstract and esoteric, but no less important than Newton, and the fact that, unlike the people that are working in that kind of thing nowadays, well, Stephen Hawking was, who passed away a few years ago, everybody knows about him. Maxwell was living at a time when that kind of scientific celebrity just wasn't a thing.
And the time he lived, what was the sort of time frame? When did he live then?
Yeah, sure. So he was born in 1831, so 2031 will be the 200th anniversary of his birth.
What was science like then?
Yeah,
what was the scientific sort of community like? Were they out there challenging? Was there different factions of scientists that sort of had different theories and were working?
There were, and that's all part of the cut and thrust of how science works. But I suppose the overarching thing to say about back then is that not everybody could become a scientist. It wasn't something that kids would be encouraged by their school teacher, well, sticking at school and you could become a scientist. Right. To some extent, you could argue it's still not really like that, but it was very much something that was done almost by amateurs, if you like. So what I mean by that is it's not that they weren't well trained and extremely clever people, but there wasn't the same kind of, for want of a better word, infrastructure around it. Nowadays we've got universities with big science departments. That was true to some extent back then, but the routes into science as a career were a bit narrower, and I suppose, to put it bluntly, that meant that if you didn't have the money and resources behind you to support going into science, at least at first, so one of the things that Maxwell also did along the way, we haven't really talked in detail about his discoveries, but we'll get to that. But towards the end, because he was very good at getting on with people, although he died young, he still managed to cram into that short life a period towards the end of his life where he was put in charge of setting up a laboratory in Cambridge. This is called the Cavendish Laboratory nowadays, and it's still one of the sort of top places to do scientific research in the country. And that kind of creation of, if you like, a national laboratory, it happened to be in Cambridge, but it was driving the innovation and ideas of science all across the country. That's much more like the modern day picture, where you've got a research council or several research councils that are looking at grant proposals that come in from scientists, and they're charged with deciding which are the good ideas and which are the not so good ideas. Sometimes it's hard to tell, but you've got to have that pipeline of funding things, and at all costs, sure, but there's very good figures on this that indicate, really for every pound that you invest in fundamental science research, you're going to get 10 times, 20 times that back in the long run, just because of all the benefits that it gives us. And that's everything from, say, the vaccine program to your mobile phone. It all ultimately you can trace back to that kind of fundamental research.
Wow. And what did so going back to the real basics, what did
he actually do?
What did he discover?
Absolutely. So he was mainly working on the theory side of things. He liked building experiments, and we're here in Maxwell's house. We do visits to the public by arrangement here. We're hoping to open that up to be a bit more regular now that we're emerging from COVID. So there's lots of bits of kit around the house here that Maxwell built himself and used to demonstrate the theory, but he mainly, I think, thought of himself as there scribbling the equations and just thinking about how things are. And what he focused on above all was trying to understand electricity and magnetism. So there'd been a lot of work done by people prior to him which had understood sort of when things get electrically charged. Everybody might remember doing an experiment like this themselves at school. The teachers used to love it, where you get something called a Van de Graaff generator, and it generates a lot of static electricity, and then if you touch it, it will make your hair stand on end. So your hair's not long enough for that now. So the understanding of electricity at some level goes back a long, long way. Thousands of years, people had an appreciation that if you rubbed certain substances, you would build up a static charge on them. Magnetism, similarly, we had a kind of rudimentary understanding of for thousands of years. A long time ago, people in China, for example, knew that certain types of metal could be magnetized, and that ultimately that led to things like, a magnetic compass to help us find our way around. But understanding what magnetism really is and what electricity really is, that was much more recent. And people were starting to put the pieces together just around, the late 1700s, early 1800s. And then Maxwell made the big leap to join the dots, if you like, to realise that electricity and magnetism are kind of two sides of the same coin. The electricity is to do with charges, what nowadays we call electrons, little particles with a negative charge. And if they're static, if they're just kind of sitting there, then that will generate what, in Maxwell's language, we call an electric field. Whereas if they're moving charges, then that's generating what we call a magnetic field. And what Maxwell did was complete the kind of jigsaw of pieces to understand how changing electric fields can generate magnetic fields, and vice versa. Changing magnetic fields can generate electric fields. So instead of being two different things, they're really just two sides of the same coin.
And
we're into quite deep water already, I know.
Yeah, we are.
Probably time for a sip of whiskey, I think.
Absolutely. Yeah, Joy, have you had a sip yet?
Yeah, I have.
No, I need to.
So maybe you begin to see why Maxwell isn't that well known, because straight away we're diving into quite esoteric ideas.
Yeah. And my immediate thought on it is he can't obviously have just woke up one day and come up with that. So, and you mentioned that other people involved in that process, and he took a leap. What was the process? Who was involved, and what was the process before
Excellent
that?
point. I say a lot of the time in science, the way that progress is made is that you have some people that conduct experiments just to sort of try things out, to apply a wee bit of curiosity, a bit of ingenuity to try and see if they can work out what's going on, and then the results of those experiments can guide us in trying to find the real underlying ideas. So, I mean, gravity is a good one. If we just briefly go back to that, I've mentioned about the apple falling in Newton's head. Well, nobody knows if that really happened, but for like thousands of years,
it's a good story.
I always wonder that. Was it as literal as that, or has that been made up as
we think it's been made up
as a demonstration, a visual sort of
exactly, and it's a good metaphor for the fact that Newton was building on the fact that everyone experiences gravity in their everyday life. So for thousands of years, people had been thinking about, well, what happens when stuff falls? And very clever philosophers like Aristotle had a certain view of what happens when things fall. His view was that heavy objects fall faster than lighter ones.
Yeah.
And then Galileo came along in the early 1600s and kind of challenged that view. And again, there's another Shaggy Dog story there where it's claimed that Galileo was dropping cannonballs from the top of the Leaning Tower of Pisa. Again, we don't really know whether that actually happened.
And that was them just theorising in their own minds, them looking at something and having a different opinion on what was
and
the
maybe
generally
we wouldn't use the word
accepted.
theorising, because in a sense, I mean, we often use that word in that context, but I think a better way to put it is that they were experimenting, because Galileo was not content just to sit there and theorise. That's certainly the right way to see it for Aristotle, because the Greek thinkers would be inclined to just kind of scratch their beards and
just think of ideas and then
But Galileo was much more into, let's try it and see what happens.
Okay. Was that just per person, or was that cultural?
Good question. I think it was partly cultural. I think, I mean, I'm not an expert in any of that, but I read a lot around it, and people that are historians of science, talk about the Greek worldview being kind of top down, that there was a certain philosophical view of how things were supposed to be, and therefore nobody bothered to check whether the reality actually matched that.
Just thought about it, decided that was what it was, and everybody accepted it.
Exactly.
And then you got more experimental.
You did indeed. So the Renaissance and the flood of new ideas about all sorts of things that were popping up around the world created the kind of conditions for Galileo to just try stuff out, But he was very good at doing the thinking as well. And in particular, his view was that falling objects fall at the same rate. So I'm not going to risk spilling any whiskey, but if I was to drop this and say drop my phone, they don't weigh the same, but they would drop towards the ground at the same rate. So Newton, when he comes along, already had a lot of those ideas to build upon, and then had to kind of weave into it the maths to describe what could be going on. And then a wee bit later we'll maybe get to Einstein as well. So Maxwell was in between Newton and Einstein, and he was kind of very much doing the same, but for electricity and magnetism. He was taking the experimental work of people like Cavendish or Ampere or Faraday were some of the names involved. I guess, you know, these are even less well known than Maxwell, but within the field of physics, these are well-known people who had got so far just by trying experiments and trying to see, well, how does a current behave when you bring a magnetic, you know, material close by, when you bring a magnet close by? But the real genius of Maxwell was to take the ideas that they'd sort of put together, got them so far, and just join the dots between them to come up with some underpinning equations, which do look a bit scary. But the basic idea is what I said a few minutes ago, is when you have a changing electric field, that generates a magnetic field, and vice versa.
And there's a couple of things that, I don't know if you've got, there's a couple of things that I want to just address quickly. The gravity thing. Two objects, if you drop two objects at the same time, they're going to fall to the Earth at the same speed, no matter what the weight.
That was
the same acceleration. They will speed up, right? But they'll accelerate at the same rate. They'll hit the ground at the same time. Now, let's say you took a feather and a hammer. They wouldn't hit the ground at the same time because the feather has got air resistance to slow its fall down. But there was an experiment done by an Apollo astronaut on the moon where they actually took a feather and a hammer, and because there's no air resistance in the moon, because there's no atmosphere, they really did hit the ground.
So the air resistance is what changes.
That's what slows down.
That's crazy.
What I was going to ask was, and that, to be honest, the feather and the hammer was the thing I went to straight away, and I thought, does the feather eventually reach at the same? Is there a terminal velocity for all objects?
Well, if you drop it from high enough, then yes.
It would eventually reach them.
Absolutely. I mean, this is why if you go to a big skyscraper, you know, not that maybe anyone would want to, but they are very, very careful to make sure that someone doesn't even drop like a 5p piece from the top, because by the time that's dropped through a few hundred meters, it's going to be going at a hell of a speed. But actually, eventually, it would reach a point where the air resistance upwards, the force due to that would be balancing the gravitational force downwards, and then it reaches what we call the terminal velocity.
Which is like squirrels.
Sure.
A squirrel could fall from. Correct me if I'm wrong. You're the scientist. A squirrel could fall from a skyscraper and survive.
To be fair, that wasn't quite what I was thinking, and I don't suggest we try that experiment just to check.
Sorry,
but I was thinking of like a flying fox.
That's what I've got in my head. Yeah.
Because what they have is like, well, I'm not a biologist, but I think they've got. It's not like a membrane, but it's basically skin that acts essentially like a parachute.
That was the animal I was thinking of.
Right. I'm relieved to hear it.
Because been throwing squirrels off skyscrapers.
Because they can survive their terminal velocity, the speed at which they.
So ultimately, it doesn't matter what height it is, because they reach that velocity and they can survive that velocity, and that's it.
Yes.
Well, again, you can parachute from a very big distance up. There's what was his name? Felix Baumgartner was the guy that, you know, from 100 kilometers, some absurdly big distance up. Crazy. And just essentially stepped off the platform and dropped. Now, of course, he didn't have the parachute for a long way down because there was no point. There was no air. But once he hit the atmosphere and the atmosphere became thick enough that the air could help slow him down, then that's when you open your parachute and eventually you reach a terminal speed.
This obviously is nowhere near my area of expertise.
This is exactly why you're here.
Exactly. If a feather and Felix dropped at the same time until they hit the air resistance, they would have fallen at the same. Or was he not that high? Was it high enough for that?
No, I mean he would have been. I think I'm right. I've remembered rightly that it was 100 kilometers or thereabouts that he was falling from. It might have been a bit less, but basically he was high enough up that there was really no air to speak of at all. That's why he had to have a pressure suit on. So it was only when he was maybe 10 kilometres up or so, 15 maybe, I'm not sure. I mean, again, you know, look at the guys that climb Everest. They've got to have oxygen as well. The air's really thin when you're that high up. So that means that the only real force acting on the feather and Felix at first would be gravity downwards. But once the atmosphere gets a bit denser, then there'll be an increasingly big force upwards due to air resistance. And then when those forces balance, one of the things that Newton brought to the table was the idea that if an object is experiencing kind of balanced forces, then it won't speed up or slow down, it'll just go at a constant speed. So in this case, that's what we call the terminal velocity.
Yeah.
So you drop a feather and Felix out of that spaceship at the same time, they're falling at the same rate.
Until the atmosphere...
Until they hit the air.
Yeah, air that's thick enough to start to slow the feather down more than him, because, aerodynamically, especially if he's pointing down, I think it was sort of head first. It was scary
stuff. It was crazy. I remember watching it live. He just swan dived.
I was pretty young when it was going on. Yeah. I was obviously still at school, and there was a Twitter account in his name, and folk were believing that he was tweeting from up there. So funny.
Yeah, I don't think he would have got the Wi-Fi coverage.
No.
Yeah.
So James, you mentioned another name, Faraday. Is that Daniel Faraday?
Michael Faraday.
Michael Faraday. Who's Daniel Faraday? Is that somebody famous?
Don't know.
It's probably sure, might be.
Rock star or something. Just cut that bit. So Michael Faraday, I recognise that name. He was involved in the same sort of type of field of work?
Yeah, he was very, very good at building experiments and making careful measurements. He wasn't quite so good at the deep thinking and the theory as James Clerk Maxwell. So Faraday had come up with some pretty good insights as to what was probably going on when you have these changing electric fields, all those ideas. But codifying it into the kind of language of maths, that's really the key step that James Clerk Maxwell did. Now, you might think, well, so what? What's the point of that? But the real breakthrough was to come when you sort of like join the dots the next level up. So what he had was a set of equations that described the relationship between electric and magnetic fields, but there was a way to put those equations together, and what you wound up getting was something that looks like what we call a wave equation in maths. So it's just a particular form of equation that describes how waves behave. Those could be water waves, they could be sound waves. In this case, well, it was a new sort of wave that people hadn't really thought of before. So we call those electromagnetic waves, and they are basically light. The light that our eyes receive is one form of electromagnetic radiation. There's a whole bunch of others, including some that were discovered after Maxwell died, like X-rays and gamma rays. But what Maxwell kind of deduced was that the mathematical equations told him how fast these waves were traveling. And meanwhile, for more than 100 years, astronomers had a good stab at estimating the speed of light. Now, again, we don't need to go into the details of that, but it's basically kind of using the fact that stuff in our solar system is pretty far away. So if you look at things happening when the Earth is on one side of the sun, maybe I can use my whiskey glass. If that's the sun and that's the planet Earth, then the Earth's going round the sun. Mm-hmm. But the planet Jupiter is going round the sun as well, so are all the other planets. So sometimes we could have a situation where the Earth is on one side of the sun and Jupiter's on the other side, or you could have the Earth and Jupiter on the same side. If it's Earth and Jupiter on the same side, then the time it takes the light to get from the Earth to Jupiter isn't quite as long because it's not got as far to go. Okay. So astronomers, starting with some astronomers in Denmark, Romer and colleagues, they'd been able to work out in the 1600s roughly how fast light travels. Not like super precise or anything, but not bad. And very fast indeed, with modern day measurements, 300,000 kilometres a second. Very, very fast. But the really neat thing was that Maxwell realised that the maths of his equations of electromagnetic waves, the maths told him that those electromagnetic waves also had to travel at this speed. And he thought that's too much of a coincidence. It must be that light is an electromagnetic wave. And that opened up a lot of new ways to understand how light is produced, how light can be manipulated, which ultimately led us to things like microwaves and, mobile phone technology. Not that Maxwell was directly responsible for those, but he opened the door to it because of understanding the nature of light.
The underlying theory of it was done by him. I was going to ask, what were some of the early uses or the early sort of inventions that came out of his work, or what was the next step?
It's a great question, because I suppose for Maxwell himself and for a lot of people at the time, they weren't really thinking in terms of there being uses. It was just neat that you could understand something fundamental about the universe. There was a scientist called Heinrich Hertz, for example, who did some experiments just a few decades after Maxwell died. And what he was trying to do was to produce radio waves. So if we just back up a sec, we talked about how electromagnetic waves are produced when you've got a changing electric and magnetic field. Okay, that's a bit jargony, but like an electric field, that would be produced by electrons. So if you can make electrons move up and down a wire, you'll be changing the electric field. So you should be producing electromagnetic waves. So that's what Hertz did. He just got electrons to kind of oscillate up and down a wire. That's how we produce radio waves. It's how, well, not so much now because we're all switching to digital, but back in the analog days, that's how radio stations would be pumping out their signals. They would be making electrons accelerate in a transmitter, and then that would send the radio waves out. So straight away, that was a pretty useful application.
Yeah.
But the stinger is that Hertz only really did it because he just wanted to check that Maxwell's maths was right. It's not that he thought of the application. But then, of course, it wasn't very long before others realised the commercial potential of this. People like Marconi, so the chain of kind of reasoning from Maxwell doing the maths part to being turned into a practical commercial application was only a few decades.
Wow. I always think that about sort of mathematicians and physicists, but especially back in those early days, it always seemed to me that they were just doing this, they were creating problems and solving them just almost for fun.
For fun, well, absolutely. I mean, it's very, very true, Simon. That goes back to what we were saying at the beginning about how the whole setup of being a scientist was different. It was almost just like a hobby, you know. So I mean, if somebody didn't have the financial resources to support themselves, I mean, it was a bit different for Maxwell once he got a university appointment, but there'd be a lot of people that, would do useful things in science, but they were just doing it for fun. You're right.
Is that something you think you're born with? We kind of brushed over in one sentence who you are and your titles and whatnot. I'd like to get back to that eventually.
No problem.
Absolutely.
But do you think when you got into it, when you obviously you're passionate, you can see it within 5 minutes, it's something you're passionate about. Is that the same thing that you're born with? It was never like I want to discover this because I want this to happen, if that makes sense.
I absolutely agree, Harvey. And I would go much further. I think almost any child has that curiosity.
Yeah.
I think sadly maybe our formal education system beats it out of them. But I think that innate curiosity that Maxwell had, that I had, still have, I think almost anybody does. So, I mean, when I do a lot of engagement with schools, sometimes it's just me doing a talk, but more often than not, it's just me answering questions or trying to help the school children answer their own questions. Because, I mean, you could go for hours and hours in a primary class just saying, right, who's got questions about space, who's got questions about science, and you get all sorts of stuff.
I'm the primary school kid today, for sure.
Sure. I mean, in a sense, I am too, because I've just never really lost that innate curiosity. I suppose what I've come to realise is that if we really, really want to answer those big questions, then you need equipment, you need infrastructure, you need organisations. I'm wearing my sweatshirt. This is Laser Interferometer Gravitational Wave Observatory. This is, these are billion-dollar pieces of kit.
Yeah.
But
that jumper.
Sadly not. But the people responsible for all of that, like me, probably got interested in science just from that childlike curiosity.
So that leads me on to a question then. Here we go. What would you want to discover more than anything else then? What are you most curious about?
That's a great question. I mean, in some respects, I'm in that very fortunate position where I've achieved my ambition, if you like, because if you'd asked me that question about 10 years ago, I would have said, I would love to discover gravitational waves, to be alive when we discover them. I know we haven't really talked about them yet. We've talked a bit about electromagnetic waves. So these gravitational waves, these come out of Einstein's theory of gravity, which is a little bit different from the idea of the apple falling in the tree. I mentioned the word forces a few times. We talked about forces in relation to terminal velocity as well. That serves us very well. I mean, it lets you work out how a whiskey glass will fall, how your squirrel will fall, how you could send a rocket to the moon and back. Newton's description of gravity is perfectly good for all of that. But in some ways, it's philosophically a bit kind of unsatisfactory because, yeah, you can write down equations about the force between different bodies, but how does gravity actually get from the Earth to the moon or from the Earth to the squirrel? You know, it's not as if the squirrel's been pulled down by a big piece of string, you know, but somehow gravity exerts an influence on the falling squirrel. So Einstein came along and actually building on some of Maxwell's ideas, came up with an idea of space and time that was very different. And we think of gravity now as the bending of space and time, you know, which as if Maxwell's ideas aren't mind-bending enough. Now we've got that to contend with. But anyway, we can maybe dig into some of that in a minute. But to answer your question directly, Einstein's theory predicted the existence of a different sort of wave called a gravitational wave due to changes in the curvature of space-time, just like electromagnetic waves are caused by changes in electric and magnetic fields. Gravitational waves are produced by changes in gravitational fields. So long story short, we have now discovered them. And I mean, I grew up reading about some of this stuff and thinking, wow, that's pretty cool. But I'm greatly privileged to have been part of the team of scientists that made that discovery in 2015. It was awarded the Nobel Prize for Physics in 2017. So, you know, it's not as if that's me done and I can just retire now. There's lots more to do. It's just the beginning of a new field. But the big breakthrough has happened. And again, it's so exciting to have been part of all of that. So if I was to think of, right, what next? You know, what would be the next big thing? Well, I don't work on this, but I think as an interested bystander and someone who's in the same general field, the field that interests me most is there life on other planets?
Yeah.
So I would love to be alive when we can definitively answer that question. Hopefully, yes. I suppose we could never really definitively answer it no, because there's always a chance we'll find it
for sure,
some other time.
Yeah.
But we're certainly getting close to the point where we could answer that question. So for me, you know, I don't work in that area of astrophysics, but having, you know, ticked off the gravitational waves one, I hope that somebody else will be as lucky as I was to be part of that discovery when it comes to discovering life on other planets.
That's got to be up there with the best answer, right? Because you can't argue with oh, well, I would rather, you know, invent shoes that tied themselves kind of thing. It's like that. You know what I mean?
I think they've been invented. Nike have got those ones that you press a button and they just go.
Absolutely, yeah.
Just
like Back to the Future.
Just like Back to the Future. They created them in real life.
It trumps anything though. Life.
Same.
Well, I was thinking, what is it? And that's kind of it wasn't Nike laces, by the way, but that trumps kind of anything I was going for.
I think it might have been Nike laces until Martin Hendry.
Well, in a way, it ties back to what I was saying about going into particularly a primary school class. I mean, secondary school, high school science students, you can start to dig into some of this stuff about Maxwell and Newton because that's what they're learning about in their school course. But even at primary, you know, even if they're like 5 or 6, they've got some idea about aliens and about, you know, spaceships and stuff. And the great thing is you're not telling them stuff. You're inviting them to say what they think because nobody knows if there's life on other planets. We've got an idea, but their view's valid as well. And you can say, well, what do you think? And then it's really interesting to see what they come up with as to what they would imagine life on another planet might be like. And then that lets you dig in a wee bit to the science, because if it's like stronger gravity than the Earth, then they're not going to be tall and thin, you know, all these sorts of things. But yeah, I just love it as a topic, as a kind of conversation starter.
Oh, for sure.
Yeah,
it's one of the best.
I think it would be kind of, is there something else out there, or how did we begin?
Well, exactly. That's what follows on. One of my big heroes in astronomy is Carl Sagan. So he was around in the 70s, 80s, 90s. He passed away in 96. I never got the chance to meet him like one-to-one, but he did come to Glasgow in the 80s when I was a student and did a series of public talks, and they were fantastic. And he said in those talks a line that ultimately made its way into the movie Contact that was based on his book. And he just sort of put it in these blunt terms. He said, well, it's such a big universe. There's so many stars and planets that if it is only us, it feels like a terrible waste of space.
Yeah,
And I thought that was a good
quote.
line. You know?
It's funny you mentioned Carl Sagan. Actually, we were talking. We got pretty eclectic on one of our live streams recently. Started talking about the fourth dimensions and tesseracts and all this kind of stuff. And I probably made a horrible job of explaining it. So it might be worth might be worth going back to that, because if anybody watched the live draw and is then going to watch this, they'll be like, oh look, there's somebody that actually knows what they're talking about. They might be able to explain it to us properly.
I started looking at like Paper Mario and stuff like that to try and work out how it.
Well,
that's right.
I could recommend any of your followers, if they haven't seen it, watch the Christopher Nolan film Interstellar.
Exactly.
Yeah.
The exec producer of that is Kip Thorne, who was one of the people that got the Nobel Prize for our LIGO discovery.
Wow. Oh, wow.
And somehow in his spare time, he found the time to be exec producer for Nolan. But he also was science advisor for Carl Sagan's book and then the movie Contact.
Oh, wow.
And Sagan wanted some kind of plausible or semi-plausible way to get people, halfway across the universe. Okay, you can just pull a McGubbin like warp drive or hyperspace, but Sagan wanted something a wee bit more plausible, and he contacted Kip Thorne to see what Kip Thorne could come up with, and actually Kip came up with something that wasn't just like vaguely plausible, but even possible. The drawback is you've got to find yourself a black hole and sort of squeeze your way through a wormhole, and things that we might never be able to do because they're not exactly in our backyard. But if you have seen that movie Interstellar, that's kind of the setup there.
I've never seen Contact, but I've seen Interstellar.
Yeah, Interstellar is one of my favourites.
At the risk of a spoiler, for anyone that hasn't seen it, there's a neat trick where people from the future basically make it possible for the people from the past to travel.
Well, that's if time travel ever exists, it's always exists.
Why are they not here yet? That's often what, and that's a variation on the other one to do with life on other planets, where Enrico Fermi, another famous physicist from the 20th century, had said, well, where is everybody? So his problem with the idea of there being a universe teeming with life is, well, why haven't we found them yet? Well, of course, some people say we have, all the alien abduction stories. I don't know what to make of them, but again, we've been asking these questions for such a short time that I think, we just need to wait. We just need to be a bit patient. But the trouble is, in answering your question, I want to still be alive when we get the answer to these questions, so the clock is ticking.
Yeah, totally. It's funny, it's come up. I'm glad this is the first whiskey before coming out with this, because it's something, I've mentioned it a couple of times now, but normally it comes out after I'm a little more intoxicated, if you like. So I'll try and word it better than I have before. It relates back to the question that I asked you, probably, is kind of what would you like to discover? Time travel is probably up there for me as well. Now,
I think it is. I mean, again, I'm not sure. Yeah, I'm not sure where I stand in that one. I think the odds in favour of there being life somewhere else in the universe, I think, are overwhelmingly good.
Yeah.
It's just that the universe is a big place that might be very far away. So, that's why I don't have a problem with the Fermi paradox, because, the nearest star is 4 light years away. So it's perfectly possible that there's life out there and it's just too far away for us to interact with. The time travel one, I recognise that it may just be that we never discover how to do that, but boy, would I love to. I mean, absolutely. Yeah.
Well, here's my little theory. If I can live to say 80 years old, 25 now, in that time I've set myself a challenge to do something that, if in a million years time travel exists, they're going to come back and find Harvey Blackie.
There you go. Yeah.
Do I think they're going to find in our lifetime? Are we going to be the age that discovers time travel? In my lifetime, probably not. Therefore, my challenge is I've got to do something. I don't know what it is. But I've got to do something that is like, I'm going to go back in time.
So just to extrapolate a wee bit on that. Right now, in human history, what do you think? Who's the number one? Who are you going back to? If time travel exists and they're looking back in all of human history, who are you going to visit? Because you want to be the guy they're going to visit, right?
Yeah.
So is it Galileo? Is it James Maxwell? Is it Einstein?
Another very famous scientist from the 20th century, Richard Feynman, his assessment of Maxwell's work was that of the entire second millennium, that people from the far future looking back, the most significant discovery of that entire millennium was Maxwell's work.
His.
Oh, really?
So by that theory, or by that, he's the guy we're going back to. So if time travel exists, they've headed straight back and they've met
this
James
is
Clerk
interesting.
Maxwell.
In a few days' time, I'm going down to Parton, which is in Dumfries and Galloway. It's where James Clerk Maxwell's buried. There's a little kirk there. And I think, well, it's early days, but what we very much hope might happen is that can be turned into a kind of visitor centre for James Clerk Maxwell. I mentioned that he was born in 1831, so we've got 9 years to get that all together. If we could have the visitor centre up and running by the time of his bicentenary, that would be spot on. And I guess what you're saying then is we can expect a few time travellers from the future to visit.
Exactly, on that day.
Yeah, I hadn't thought of that before. That's an interesting angle.
Yeah, I think it's interesting, and I've never heard. We've talked about this before, and I think it's so interesting. The point I've never thought about it like that is doing something significant enough to be the guy that the time traveller comes back to visit.
Yeah,
is a really cool. It's a really cool.
I've not been travelling at all much in the last 2 years, as none of us have because of the pandemic. So one of the kind of family memes is that I would always say, "Oh yeah, I saw that on a plane," when people are saying about films. Yeah. So I've been a bit out of step with that, but I was flying to the Middle East last week for a science festival.
Cool.
And it gave me a chance to watch a few movies on the plane. Nice. And one of them was Bill and Ted Face the Music. And that is very much cut from this mould, and them having the weight of future history on their shoulders, thinking, well, we've got to do this thing, because if we don't, then all these people in the future that look back to this thing, it'll all fall apart. So good luck, Harvey.
Yeah, thanks. I've no idea.
Got to write a pop song. Killer rock
I've no idea what it would be. I'm not going to.
You've got like 60 years to just change the face of the planet, change the trajectory of planet Earth and the human race.
We'll see.
60 years.
Challenge accepted.
Good luck.
Challenge accepted.
Good man. I want to just go back a little bit, if that's all right, because we and as is the case, I've taken a couple of wee notes, because as is the case with these conversations, you can skirt past like huge topics in like one or two sentences, and the gravitational wave stuff, which you're involved in, the LIGO stuff, which is just amazing, and congratulations on your MBE as well. I want to go back to that, if that's possible.
Of course.
Einstein, I'm going to say theorized again. Is that the right phrase?
No, that's certainly correct in his case.
This time Einstein theorized it. Was he the first person to come up with this idea? How did he come up with it? And what I can never get my head around is, what was he just doing the dishes one day, and then he just thought, I tell you what, how does gravity get to the squirrel?
It is a great question. And the reality, of course, is that there was a lot of work that he built on. But the popular mythology around Einstein is very much him as the lone genius, and I'm not sure how helpful that is, because, he was very much an outlier when it came to his brilliant insights. But it kind of suggests that, nobody else could have done it. Whereas actually, I think if Maxwell had lived another few decades, he might have got there himself.
Yeah.
And if not, then if Einstein hadn't been born, somebody else would have. It might just have taken us a wee bit longer. Yeah. So the kind of foundations that Einstein was building on involve ideas that go all the way back to Newton and even before to Galileo and others. But they also bring in some strands from the more contemporary times when Einstein was around. So this is like late 1800s, early 1900s. Still feels like a long time ago, of course, but nonetheless, the ideas that emerged from all of that were sufficiently revolutionary that they're absolutely still at the cutting edge today. So what exactly are they? Well, it's about notions of how we measure things in space and time. And Newton had very much grown up in a world where space and time just are. They're kind of fixed. They're like a stage, like, all the world's a stage. The events of the universe just play out on that stage. And the way that I like to develop, how Einstein went beyond that very much brings in James Clerk Maxwell. And that's not just me being parochial. Einstein name checks James Clerk Maxwell in the first sentence of his key paper on his theory of relativity. So, that connection is clearly there. But I'm still like oversimplifying a little bit, just the kind of chain of reasoning, just for speed.
You can't oversimplify it for me, so don't worry.
Yeah, don't worry. We can. It's an interesting topic.
So you can kind of think of it like this. I mean, when I'm talking about this stuff, as I will be down in Parton, where Maxwell died, next week, or when he's buried, I often portray it as a kind of like a conversation between Einstein and Maxwell. So that never actually happened. But if it had happened, then it would have involved Maxwell explaining that light is an electromagnetic wave, like we were discussing before. And you might remember I was saying that electric fields are like to do with static charges, and magnetic fields are to do with moving charges. But the thing that Einstein had a big hang-up about is, well, who gets to decide who's moving and who's static? So, like, if you're on a train, like me coming through in the train today, if there's another train at the station, sometimes it can take you a second or two as you look out the window to work out whether it's you that's the one that's moving away from the station or the other train is. And that was Einstein's big point, that we ought to be able to describe how things work without getting too hung up about who's the one that's static and who's the one that's moving. So there's a lot of maths detail comes from that, but what it really boils down to is this. This beautiful set of equations that Maxwell came up with describe moving charges and static charges. And Einstein wanted those equations to work regardless of who's the one that's moving. So if you're in what scientists call a different frame of reference, like a different point of view, then that would mean that the charges you previously thought were sitting there, not moving, well, now they are, because you've changed your perspective, you're moving yourself. Another good way to think about that is, if you're like in a car in the motorway and there's a car in the adjacent lane, if you're both going at the same speed, it sort of looks as if you're not moving, because you're keeping pace with each other.
So you're static, the other car's static, and the rest of the world is moving.
Exactly.
That's how it appears from that.
That's how it appears from that point of view.
Is that general relativity?
That's special relativity. So special relativity is all about moving at a constant speed, and the kinds of changes in our perception of space and time that result from Einstein's desire to have everything work regardless of how fast you're moving.
Was there a thought experiment that Einstein did around a rocket ship and shooting?
Yes, we're just coming to that.
Because I've heard this before and it blew my mind.
That's perfect, because that's exactly the next step. So Einstein realised that in order to preserve the wonderful structure in Maxwell's equations, then what he needed was for the speed of light, which is the speed of the wave in Einstein's equations, in Maxwell's equations, he needed that speed to be the same for every observer, regardless of whether you're moving or not. Now that's weird. Normally we think, if say you're on a moving train and you run along the corridor of the train, then your speed with respect to the platform is a wee bit faster because you've got the train speed plus a bit more of your own. What Einstein's equations say is that if you shine a torch on a train, then the speed of the light beam from the torch, as measured on the train or as measured from the platform, are exactly the same. But what I'm emphasising is that's not just an accident. It's not just something Einstein thought up, on a whim. It's because it was the only way he could preserve the beautiful structure of Maxwell's equations. So that's why he name checks Maxwell right at the outset of all of this. But the consequence of that, of making sure that the speed of light is the same for everyone, is that our measurements of space and time are not the same for everyone. So if you're travelling faster, time seems to run at a slower rate.
Right.
Your perception of the size of an object is affected. The actual size of the object isn't, it's just how it looks to you. I mean, a good analogy I often use is, like, in normal space, in 3D space, I tilt my phone, the phone's still the same size, even though it looks a lot thinner now to you than it does when I do that. Mm-hmm. So we're kind of used to interpreting what our eyes see in different ways depending on the point of view. It's just that when you add time into the mix, it gets even weirder, and we're not maybe so used to thinking about that. We normally think of time as just flowing at the same rate for everyone, but it really doesn't. Time runs at a different rate depending on how fast you're travelling. Now, where the thought experiment you were talking about, where that comes in, is when you try to bring gravity into the picture.
Yeah.
And the big breakthrough that Einstein came up with was that gravity and acceleration are really one and the same. So if you imagine, sitting in a very fast car and, gunning the engine and off you go, you accelerate up to like 60 miles an hour in no time flat, you'll feel yourself being pressed into your seat. The same if you're on an aeroplane as it's accelerating along the runway. So that's the sensation of acceleration being a bit like the sensation of gravity, giving you a feeling of weight, of being weighed down. And Einstein basically figured that gravity and acceleration aren't just like similar, they're actually identical, they're equivalent. So if you were on a rocket ship that was accelerating and you let something go, it will fall to the floor of the cabin. If the rocket ship was on the ground and you hadn't even switched the engines on yet and you let something go, it would still do the same. Now, of course, you would kind of know if you were out in space, you could look out the window, you could feel the rocket vibrating. But, leaving all of that aside, it was just like in a closed room with no windows and it was all...
You wouldn't be able to tell the difference.
You wouldn't be able to tell the difference. And that unlocked for Einstein an ability to describe gravity and acceleration, not as a force, but as a curving of space and time. And then what followed from that was the prediction of gravitational waves. So there's a connection to Maxwell and the ideas about electromagnetic waves that ultimately lead to these gravitational waves as well. And that's why, for example, gravitational waves are predicted by Einstein's theory to travel at the speed of light, the same speed as light waves, because they've kind of emerged from similar phenomena from the structure of space and time.
Yeah. Wow. I've got so many questions I want to ask.
Yeah.
I've got one. This might sound absurd, and I may be completely just off on the wrong tangent, but I'm just trying to think. If it was possible for me to travel at the speed, you said light travels at the same speed regardless of what viewpoint you're looking at it from. So if I'm traveling at the speed of light myself, and I turned on a torch, what would happen to the light coming out of the torch? Would it then continue to travel at the speed of light ahead of me?
Well,
or would it just sit next to me? How would that work?
Well, this is what led Einstein
silly, but...
to unpick all of these questions was like you were saying, was he a theorist? Yes, he absolutely was. But there's a neat phrase that we use called a Gedanken experiment or thought experiment, which Einstein was especially good at. So he was still basically just sitting there thinking, but he was imagining a scenario that in principle you could do. You could build a spaceship and fly it very close to the speed of light and shine a torch. What would happen?
Yeah.
So he was trying to understand, well, what would happen? So actually that takes us back to the whole thing with Maxwell, the static and moving. Einstein was saying, well, if I could travel alongside a light beam, would it still be a light wave? Because it would be like frozen, just like the two drivers in adjacent cars in the motorway. Yeah. And because he knew that would make Maxwell's equations sort of fall apart, then he concluded, well, actually, it still would be a light wave because it would still be traveling at the speed of light. So the answer to your question is yes, it would. You would, even though you yourself, well, technically you couldn't travel exactly at the speed of light because you're a massive object, but you could get as close as you like to the speed of light and you would still perceive the light beam to be travelling at the speed of light.
Moving away from you at the speed of light.
Yeah. That's weird, it's contrary to our everyday kind of intuition about how the world works. But the world that we experience is where everything's going pretty slowly. And if you look at the kind of experiments they do at CERN in Switzerland, or even experiments involving atomic clocks that they've flown on board spacecraft or aircraft, we can be moving fast enough that you can notice these tiny differences. And Einstein is always on the money, that
and he was right with all these sort of
ideas. Yeah. So in fact, the GPS on my phone, that only works as it does because the difference in the rate at which time flows in the satellites up there is accounted for compared with down here. Now it's only microseconds a day, but light or radio waves can travel quite far in a millionth of a second. So if all of this wasn't correct, then your mobile phone wouldn't work. Well,
you'd be out
at least your GPS wouldn't work. Exactly.
Whereas it's to a meter.
Yeah.
You can pinpoint it.
Yeah, sure.
Whereas it would be out by a mile or 100 miles or whatever.
So, I'll occasionally in public talks, I'll get people that say, I don't believe all this Einstein stuff. I say, well, have you got a mobile phone? Well, and they say, yeah. And I say, well, how did you find my lecture tonight? And okay, that's a bit provocative, but then you can just unpack it a bit as to, it's no longer the case as people might think that all these ideas of Einstein are just, crazy theories. They are now tested and underpin a lot of the technology that we use. And then, of course, we can now test them by looking out at things like colliding black holes that, our LIGO instruments can measure. So, yeah, I mean, it's not a complete theory. There's still issues with some of the details. And another big, very important area of technology for modern physics is what we call quantum physics. And we don't yet have a working theory of quantum gravity. So we've not been able to tie gravity in to the quantum description of nature. Maybe that will come in the future. We might have to wait a while. But nonetheless, Einstein's theories are a lot closer to the truth than Newton's.
Am I right in saying that they don't work together? Is that right?
That's
quantum
right.
physics and relativity,
general relativity works really well on big scales, but when you go to the small scale phenomena inside atoms, then it's the rules of quantum physics seem to take precedence, and we haven't been able to reconcile those yet.
So we could get to a point potentially where we could actually, I don't know if this is going to be the case, but quantum physics, for example, could prove Einstein wrong. Eventually, or because that's what science is about, right?
To some extent, it already has, right? In the sense that what it's done is allowed us to see that in some situations relativity doesn't work,
right?
Or it doesn't work exactly as Einstein said. And Einstein had issues with some of the ideas of quantum physics, ideas about the very existence of particles like electrons or quarks and all this kind of stuff. Well, quarks came a bit later, but what quantum physics really says is that those objects, those things, in some real sense, don't actually exist until we look at them, until we try to measure them. Mm-hmm. And Einstein had big problems with that. He thought that there had to be some kind of objective reality out there, whether we're looking or not. Mm-hmm. Now, in a way, this brings us back to your question, Harvey, about the big question. I mean, we know there's life in the universe in the form of us. My instincts are that there's life everywhere in the universe, that it's not an unusual phenomenon. But mainly sci-fi, not so much in hard science, but I mean, I'm a big sci-fi fan as well. One of the ideas that's explored a lot is that, well, is the universe conscious? Is it, does it require the existence of life to make the universe exist? So there's very interesting ways to tie all this together. Maybe not so much in lectures and stuff, but certainly over a glass of whiskey.
For sure. That's what this is about. So
and I think the realization that there are severe gaps in general relativity. I mean, it bothered Einstein, but it continues to bother us, and we hope that quantum physics will be able to plug those gaps, but we've not worked out how to do it yet.
And space-time is a phrase that comes up all the time in any sort of discussion about this, can we briefly describe what that means?
Yeah, sure. Well,
because it comes up all the time. I think that there's an assumption that it's quite I'm sure it's a basic principle, but it's quite difficult to understand.
It is, and again, often all we can really do is just fall back on analogies. So I talked before about how the perception of my phone and its true size, that we're accustomed to the fact that when you look at something from a certain point of view, that its apparent size can be changed. We still know the phone's the same size. If I tilt it up like that, we see it again.
So we don't all of a sudden think
the phone's got smaller.
It's different. Yeah. Okay.
So in the same way, when you look at the dimensions of space and time together, what Einstein's theory tells us is that the dimensions of an object or the separation between events really needs to be thought about in both space and time together. And that if you just consider how far apart they are in space, then different people will reach different conclusions. Just like if I say, right, how big's the phone? And you literally just think it's what you can see, then you would think it's different now from now. But without maybe thinking about it, that the phone hasn't changed in size. It's just sort of changed its orientation with respect to you. So when you travel at different speeds through the universe, then if you think of like this dimension is space and this dimension is time, then this would be where you're seeing all of the time dimension but none of the space, all of the space but none of the time, somewhere in between. It's still the same phone in all of those situations. So what that's kind of telling us is that if we really want to understand the nature of reality, we need to be thinking of space and time together. And at certain times, you'll see only the spatial part, and at certain other times you'll have a perception of the other dimensions as well. And it's only by looking at them together that you can get the full picture.
And they have to go hand
that's
in
what
hand
we call
in
space-time.
everything. They're never looked at as individual entities, or do they have to be?
In some situations they can. So one of the things that people learn about at high school is the conservation of energy.
Yeah.
The fact that energy
never
is
lost.
Yeah, exactly. And by and large that's true, but as ever there's some kind of nuances on that when you delve a bit deeper. Another thing that people learn about at high school that maybe don't remember so much from high school because it's not done in such great depth is what we call the conservation of momentum.
Yeah.
So in Newton's way of thinking about physics, we can consider them separately. You can have the conservation of energy and the conservation of momentum. But the conservation of energy is really associated with an object that isn't moving. Again, I'm being a wee bit loose in my language, but you can think of it like that. Whereas the conservation of momentum, something has momentum if it's moving, if it's got a certain speed. So because relativity is all about considering what things are and how they behave, regardless of whether you think they're moving or not, what you have to do in relativity is look at the energy and momentum together.
Yeah.
And that gives you the full picture. And if you just look at them separately, it's not such a complete picture. However, in most situations where things aren't moving very fast, then you can quite happily look at the energy and momentum separately. It's only when you start getting close to the speed of light that you need to consider.
So the conservation of momentum, is that the theory that if you have a force acting on something, there's no other forces, it will never stop, change direction.
It's a consequence of that, absolutely. And Newton's second law, F equals ma, is how it's often learned about at school, really says that an object, unless there's a force acting on it, its momentum won't change.
It'll never change.
It'll just keep on going. But again, that's only true in the kind of low speed limit.
Right.
And if you are travelling close to the speed of light, then you've got to take a more kind of rounded look at it and look at the energy and momentum together.
Just like that.
Just easy.
And Einstein came to an understanding of all of that, but maybe not as quick as he might have, because he skipped a lot of maths classes that would have really helped him. But fortunately, one of his pals, Marcel Grossman, had gone to the maths lecture, so
he wasn't a great student, was he? Or in terms of structured sort of...
Indeed, I mean, he was good at asking really deep questions, but I think, to be fair, the German education system wasn't very well designed to answer them.
Yeah.
So often the teacher would just roughly say the equivalent of, just shut up and don't ask questions.
Just asking silly questions.
By the time he was at university, I mean, the system was a bit more like it is today, encouraging free thought and all of that. But maybe not quite enough to suit Einstein's needs. I mean, he just didn't see the point of going to lectures. He thought, why can't I just kind of learn that stuff myself? But of course, sometimes he would need an understanding of something in his toolbox that you would only get from going to the lectures.
It's interesting actually, because that kind of, like, with the best will in the world, I could be as interested as I want about black holes, but I'm never going to solve the problem. So it's like what you're saying. It is natural. I think for someone like Einstein, that's an intelligence that's there.
You never had the chance to answer that question either. What would I discover? I'm black hole daft. I would love to just get straight into a wormhole and see what happens. Survive it, get through it. Obviously, you might end up as a tiny little singularity, like a huge massive matter in an infinitely small space, but it would just be so interesting to find out what happens. So if we could solve that one, that would be mine.
Yep.
But I think also we can definitely get to that. But and that does tie in with time travel and other sort of aspects. But yeah, the black hole stuff I find fascinating. I think until fairly recently, I was never even sure if black holes were real or if they were just made up. Like, it's one of those things that just everything about it feels like it's from a sci-fi movie and it's not real. Like, there's no way we have these huge big holes sucking in mass, like in the middle of space. That can't possibly be real, but it is real, right?
As best as we can tell, I mean, we had pretty good indirect evidence for them anyway, even before LIGO came along. But when our detectors began operating, in the middle of the 2000s, then they weren't yet sensitive enough to detect anything, but we knew we were getting close. And then they were upgraded in 2015, and it was within just a few days, actually, of the upgraded detectors, more sensitive, more able to detect the tiny changes in what we call ripples in space-time, produced by things like colliding black holes. And that has helped to reinforce the belief that black holes absolutely are real, and indeed we've found lots and lots of them. Our latest catalogue, so we do this as part of a global collaboration. There's another detector called Virgo, there's another one in Japan called Kagra. So we're currently not gathering data. We'll start again in spring 23, but we published about a year ago a catalogue of all of our discoveries to date, and it's 90 different gravitational wave events, almost all of which are black holes colliding with other black holes, but some other ones where it's a different sort of weird object called a neutron star colliding with another neutron star, or indeed a black hole. So bit of a mixture.
So when you discovered that, is there a moment where it's like, boom, that's it? How I can't get my head around such a breakthrough, such a discovery. At what point is it like, tick?
Yeah, again, an excellent question, which opens up some very interesting aspects that I hadn't really thought so much about. Thank you. Time for another one.
Absolutely. We're getting into black holes now.
Yeah. So there's a very short answer, which is yes, that there was a tick the box moment. But what we're doing here is we're using lasers, hence the L in LIGO, to look for changes in the curvature of space-time in our neighbourhood, where the detectors are. There's two LIGO ones. There's a Virgo one in Italy. There's Kagra in Japan. The two LIGO ones were operating from 2015. Virgo in Italy came online a couple of years later in its enhanced sensitivity. So the very first detection, it was just the LIGO detectors in the US. So one is in Louisiana, one is in Washington State, so about 3,000 kilometres apart. And when they detected a signal, it was a change in the pattern of the laser light, what we call the interference pattern, hence the I in LIGO, laser interferometer, caused by a gravitational wave passing by and kind of stretching and squeezing space-time, but by a tiny, tiny amount, equivalent to about a millionth the width of one of my hairs. So, that's why it took us 100 years to have the technology capable of detecting this. And the other thing is, and this is, absolutely where your question is very pertinent. When you look through an optical telescope at the moon, you can just see it's there, right? Whereas the signal we were searching for, I've actually got it on my
Is that
my
the
sweatshirt.
actual signal that was
That's
picked
the
up?
pattern. So what you can see is a red and blue kind of squiggle.
Yeah.
The fact that they look so similar in red and blue, the red is Louisiana, the blue is Hanford, Washington, immediately told us, oh, there's something here, because they're 3,000 kilometres apart. So if it was just a local disturbance, what we basically call noise, rather than a real signal from out there in space, then there'd be no reason why the two of them should look so similar, why just by coincidence you got the same noise at the same time. So I was actually in China when this first detection happened, and along with a few friends and colleagues from my department in Glasgow. And, of course, we got the emails. We were on endless telecons discussing it. The point I'm making is that although it looked pretty nailed on from the beginning, we still had to quantify, well, just how likely is it that, or let's say it the other way around, how unlikely is it that you would get noise in those two detectors 3,000 kilometres apart that just happen to look the same? To get this published and ultimately to get the Nobel Prize, we had to be pretty darn sure. So even though the two signals looked very similar, and it was kind of immediately very exciting thinking, geez, this looks like the real thing, we had to do 5 months of painstaking work to try and quantify how often, just by coincidence, by bad luck, you would get noise in the two detectors that could mimic this. So that involved kind of modelling and trying to copy the kinds of noise that you would typically get in the detectors, trying to quantify how often those noise patterns would just happen by accident to look so similar. The upshot of all of that, at the end of the 5 months, is we'd convinced ourselves that that was extremely unlikely. You know, it would only happen like once every 100,000 years. So that was kind of good enough, you know. Now, if we had found that a noise pattern like that could happen just by coincidence, just by bad luck, once every 100 years, would that be enough to convince us to say, right, we've definitely detected something? Probably not, you know. Now, so we call this our false alarm rate. It's like the number of times that we would claim a signal, but it might just be a false alarm. So since we've detected lots of them now, we're prepared to reduce our false alarm rate a wee bit. Maybe I should say increase our false alarm rate a wee bit. In other words, to publish ones that might not be real, but we just want to make sure that people have got the chance to analyse the data for themselves. But for this very first one, we wanted to be super cautious. So that was why we couldn't just like say, phone up the newspapers the next day and say, we've done it. And actually, you know, there's a few examples in the history of science where people have jumped the gun, where they've claimed a result too soon and then they've realised that, well, maybe their analysis sort of missed something or overlooked something. We didn't want to fall foul of that, so that's why the long delay. So it's a curious thing. I mean, I was very excited to be involved in all of this, but we knew we had to stay calm and we had to go through a very long checklist of things that needed to be done before, you know, we could get our big moment.
And what happened? What does that signify? What happened to make that wave?
Yeah, so what that represents is the final fraction of a second as two black holes spiraled in around each other and collided together and became one bigger black hole. Each of them was about 30 times more massive than the sun. And when they collided, they gave off gravitational wave energy, just like, you know, you can get electromagnetic energy when electrons are whizzing around, like we talked about before. And you can kind of think of that as like space-time reorganizing itself. So I know that's a bit of a wild idea, but you know, if we think of a black hole, it's not got a solid surface, but what it represents is a region of space-time that's distorted so much that even light can't escape. So what you've got is two such regions, you know, whirling round each other close to the speed of light, getting closer and closer together, giving off gravitational waves in the process, and then finally merging. So the pattern, you know, where it gets like at its biggest extent, that's where they merge. And then you've just got one black hole that wobbles a little bit more and then space-time settles down again.
So does
all of that was happening.
Does one swallow the other?
Well, in this case, they were of approximately the same mass, the same size, if you like, in terms of their event horizon. So it's really more a case of them eating each other, you know, swallowing each other. But there have been other ones that we've observed now where one black hole has been a lot bigger than the other. Or indeed you've had a black hole swallowing a neutron star, and there it's maybe more appropriate to think of it like that. In fact, the black hole swallowing the neutron star has been especially interesting. We've had two examples of that, but in neither case did we see any light given off. That wouldn't have been us anyway, it would have been other astronomers looking with optical telescopes and the like. In a way, that's not too surprising. The black hole neutron star collisions were very far away, so probably any light given off would have been too faint for our telescopes to see. But it's also possible that no light would be given off anyway, because if the black hole swallows the neutron star quickly enough, then it's just gone, you know. Whereas if the neutron star gets kind of torn apart by the gravity of the black hole, then it kind of spews its guts, and that means you've got a lot of matter around, you can get gamma rays given off and all this stuff.
Well, one of the questions I was going to ask is how do you look at an object that doesn't give off light?
Well, you detect it in gravitational waves, right. But ideally, if there is any light given off at the same time, you would want to see that as well. And when two neutron stars collided on August 17th, 2017, the Virgo detector was operating by then as well. So we had 3 detectors. We could triangulate the position on the sky a lot better. And that allowed us, on the basis of there being a gravitational wave signal, to then, you know, seconds later, to detect a burst of gamma rays coming from these two neutron stars colliding together.
What's a neutron star?
So a neutron star is like almost as weird as a black hole, but not quite. If you have a big star, then you've maybe heard the phrase supernova.
Oh, these ones that implode.
Yeah, so the supernova explosion sends the outer part of the star, you know, spreading outwards through the universe. But meanwhile, the core of the star implodes, collapses. Now, if that core is sufficiently massive, then you get a black hole, because nothing can stop the collapse. But if it's a wee bit less massive, then it can reach a new balance point due to something really weird called neutron degeneracy pressure, which is associated with kind of quantum effects of neutrons being packed really close together. They don't like that, so that presents a kind of again, to use the Newtonian way of saying it in terms of forces, it gives you a kind of an outward force or pressure to balance the gravity, trying to make it collapse.
Just holds it.
Yeah, so it holds it there. So neutron stars, like a typical neutron star would be about 1.5 times the mass of the sun. So that's about 3 million kilograms, but about the size of Edinburgh, about 10 kilometres across. So these are pretty dense things,
right.
But they're not quite as weird as black holes, because with the black hole, whatever was there before has collapsed entirely to that singularity.
Yeah.
The neutron stars haven't gone that far yet. So when two neutron stars collide, then like you can in principle get light given off.
And they have mass.
They
would
mass.
actually collide two
solid surfaces.
Surfaces
would
collide against
sure,
each other.
Absolutely.
And
therefore,
an event would happen.
If you had two neutron stars colliding, like they wouldn't just like bang together like two billiard balls banging together. They would get distorted and kind of a bit torn apart first. But if it's a neutron star and a black hole, that could happen, or it could be that the black hole swallows the neutron star so fast that it doesn't have enough time to get torn apart.
Disappears.
Yeah. So the way that I like to see that in public talks is that it's like contrasting, the eating habits of Pac-Man and Cookie Monster. If it's like Cookie Monster, then it means that it's very messy, and the insides of the neutron star get kind of strewn around. We could look for that with optical telescopes or gamma ray telescopes, and that would complement the information we get from the gravitational wave detectors. But when it's black holes and black holes, it's probably just gravitational waves, and that's all you get.
And what happens to all the mass in that black hole?
Well, it rests inside the event horizon of the new black hole. Most of it does, but some of it gets turned into gravitational wave energy. So, like the two in the first event, one was 29 times the mass of the sun. We could work that out from looking at the signal, at the exact shape of the signal. And then the other one was 36 times the mass of the sun. When they merged, you got a new black hole with a mass of 62 times the mass of the sun. So you get that from the final bit there. Well, 29 and 36 is not 62, it's 65. So in the case of this one, in about maybe a third of a second, the equivalent of 3 times the mass of the sun was turned into gravitational wave energy. Now, this probably happened with no light given off at all. We certainly didn't see any. So in a sense, we really are kind of probing the dark side of the universe. And I think it was Darth Vader himself that said you should never underestimate the power of the dark side. If you look at that much energy, because you get that just from E equals mc squared, 3 times the mass of the sun, c is the speed of light, you get the energy. If all of that energy is given out in a third of a second, then power is energy divided by time. And that turns out to be about 50 times the light power of every single star in every galaxy in the entire universe. So what that's given us a sense of is how much energy is locked up in the curvature of space-time. And when these black holes collide, you're releasing that. It's like, stretching an elastic band. You've got to put a lot of energy in to make it snap. But when it does, it releases a lot of energy in the process. And that basically is why it took us 100 years to detect these. Because I can shake my fist and technically I'm producing gravitational waves because I'm changing the gravitational field of my hand. But I'm moving it, incredibly slowly compared with the speed of light, and it doesn't weigh the same as a star. It's only when you've got really dense star-like masses moving close to the speed of light that you can shake up space-time enough to produce measurable changes in the curvature, and you release a lot of energy in the process.
How many people are on the team?
I think in total there was about 2,000 authors of the paper. And then we've expanded since. So there's LIGO, there's Virgo, and there's CAGRA. LIGO's got about 1,500 scientists worldwide. I think altogether we're probably pushing about 3,000 now in total. Yeah, so it's a lot of people.
And who funds the project?
Variety of sources. So the National Science Foundation fund the 2 LIGO detectors. That's the US funding agency for fundamental science. So it's not NASA. NASA does all the stuff up in space, but the NSF does like telescopes and things like that on the ground. In the UK, our funding in our research group comes from a body called, now is called UKRI, UK Research and Innovation. But that's a kind of umbrella organisation now. There used to be, well, there still are, in a certain sense, distinct research councils. So the one that I'm part of is STFC, Science and Technology Facilities Council. So they fund my research. If you look up STFC, I mean, that's what you would find now is them. But for a long time, when it was first set up in the 90s, you got Swindon Town Football Club. But ironically enough, their headquarters are actually in Swindon, so it's maybe not such a bad connection.
That's interesting.
Yeah, there was a lot there. So many times I thought, right, I'll ask a question. Then
I had to take little notes as I went.
I realised once I get going.
No, please, yeah, don't.
It's a lot of momentum, so
it's great.
Feel free to interrupt.
No, not at all. It's just I'm liking that you've been taking your notes.
I had to, because I'm thinking he's saying that, and I'm thinking I need to go back to that because that's interesting. But go on.
The MBE.
Yeah.
Was that on the back of all of that then?
Actually wasn't. The discovery of the gravitational wave event, the first one, was on September 14th, 2015.
Right.
And I was awarded my MBE in July of 2015. So what I got it for was for services to the public understanding of science. Because even long before we'd made this discovery, what I had been leading within LIGO and then just doing locally myself with a number of colleagues was promoting this kind of thing to school children, to teachers, to the general public. I've always been passionate about it. I led a programme of, we can finally get to talk about some whiskey. I led a programme of visits to high schools in Scotland in 2012, for example, which was called Exploring the Dark Side of the Universe, because it coincided with a change in the high school physics syllabus in Scotland, connected with, you've probably heard the terminology, the curriculum for excellence that people talk about. So I was on the design team for that.
Right.
And actually one of the things that we did with a wee bit of trepidation was to change the syllabus so that we would update it to include a lot of this cutting edge stuff that, kids were hearing about or maybe reading about in the newspapers, but it wasn't in the course. And we thought, well, we're really missing a trick here. We should update it all, make it a bit more exciting, a bit more current. So I'd helped with all of that, starting from about 2009. By 2012, there was a lot of schools around the country that were already adopting this new syllabus. So that was including stuff about, general relativity, about dark matter and dark energy, about a lot of pretty, spooky stuff. And I'm delighted to say that going round the school, so I did a tour of the Hebridean Islands because I was especially aware that they don't often get a visit from people from the university, or they wouldn't often get a visit, to try and enhance what they're learning in the curriculum. And the final stop on that was Isla. So I'm sorry I didn't have longer to spend to explore more of the distilleries, but as you maybe know, Bowmore distillery is right beside Bowmore High School. So it was excellent after it. I did something, it was an itinerary that, rock groups would be proud of. I did something like 30 schools talks in 9 days across 9 islands, and the ferry schedule was meticulously planned, but it didn't let me down, so I managed to get everywhere where it was supposed to be. And then, Isla was the final stop. So it was great to have a glass of Bowmore at the end of my week and a half. But that is an example of the kind of thing, probably, you don't ever find out really what you get the MBE for. I don't even know who nominated me, but I have my suspicions.
Yeah.
But the award technically was not just for my kind of scientific research, but was for my contributions to try and share that with other people. So I had a nice wee chat with the Queen. She said, "The universe is rather big, isn't it?" And I said, "Yes, ma'am, and it's getting bigger all the time." So in just those few seconds, I conveyed the key big discovery in cosmology of the 20th century, that we live in an expanding universe. And then, she shakes your hand and then it's time to move on. So it wasn't long, but it was
Let's say I've still got enough to be cheers. Well done.
Yeah,
thank you.
Actually, Martin mentioned you had a cheers. You had a special cheers that you did.
Absolutely,
the black hole cheers, and it was. I'm sure.
So an in spiral toast. These would get closer together, and then they would clink together.
I like that.
We talked about this on our Zoom meetings.
We did. Although in a way, I mean, always happy to think of them as black holes.
You guys have little clubs I'm not invited to.
Yeah, you were invited. You were invited to that night. It was just us chatting on Zoom.
But if you think of them more as these neutron stars, because they're actually
they have mass.
They've got mass. They've got a solid surface. They've got an interior structure. So when our glasses clinked, you could see that the whiskey sloshed around.
Yeah.
And that's kind of what we're hoping to learn from studying neutron star collisions, to actually see what's going on inside the neutron star. It's like doing seismology on neutron stars billions of light years away.
Wow. Well, you segued lovely actually into another topic I was going to talk about, but first and foremost, how you find the whiskey, the Macallan?
Very good.
Always a pleasant surprise actually, and it does.
It goes down very smoothly.
Macallan gets a bit of a hard time actually, the younger stuff sometimes, but this is.
I'm really enjoying it. Yeah,
it's absolutely lovely.
I mean, I'm a fan of the peatier and smokier ones as well, but sometimes just.
Yeah, it was between Macallan and Bowmore actually, and I thought Macallan. One because it's Macallan, but 1824 is obviously a significant year for the industry. But I could have picked loads of distilleries, because 1824 seemed to be the year to found a distillery. Yeah. But it was obviously, it ties in almost
very close to when Maxwell was born, and there was certainly interesting stuff happening in the world of science around then too.
The size of the universe. You and the Queen chatting about the size of the universe.
Absolutely, as you do.
Do you know what? Actually, it was so funny. Just when I was thinking on the way along here, how am I going to start this conversation? How do you start a conversation about like the universe? Obviously, the obvious place to start was where we are, talking about James Clerk Maxwell. But I definitely wanted to ask. I was like, how does the universe start? What happened? The Big Bang. And I think about, when I think about the black holes, we're talking about that all that mass in a singularity. Was that what happened? Is it the same thing, and then something sparked? And what happened? What happened 1 second before the Big Bang?
Again, these are great questions. They tie together a lot of the strands that we've been talking about. I mentioned Hawking, and then we quickly moved on.
Exactly, yeah.
Stephen Hawking really rose to prominence because of the work he did on what are called the black hole singularity theorems. And this was working with Roger Penrose, who's still alive and got the Nobel Prize himself a few years ago. He, with Hawking, basically showed that if you start off with something like a star that's pretty spherical typically, so the kind of mathematics of that is just that it's like the same in all directions from the centre. And if that system collapses under its own weight, under its own gravity, then what they showed was that according to general relativity, there'll be nothing can stop it from going all the way down to a singularity. Now, there might be something that would stop it, but that's where we're back to our quantum gravity again. So I mentioned that in the case of neutron stars, they can stop the collapse because there's a source of pressure that pushes out. So that one we do understand, and it still sort of exists within the framework of quantum physics. It's called a neutron degeneracy pressure. White dwarfs, which is another type of very compact star, but not quite as weird as neutron stars, those can stop their collapse because of something called electron degeneracy pressure. So maybe, just maybe, there's something stops a black hole from collapsing all the way to a singularity, a different sort of quantum pressure, but we don't know what it is yet. It might be to do with, quarks or Planck masses or something. So it's not to say that the singularity theorems of Hawking and Penrose are the end of the story. They're not. But at least within the framework of general relativity, what they say is that once a spherical thing starts to collapse, nothing will stop it collapsing to a singularity. So the interesting thing is, what if you run the clock the other way? What instead if you start off with a singularity and then run the clock the other way? What it's basically saying is it ought to expand. And that seems to be what the universe is doing. So all of this, jumping over several decades and hundreds of people's work, it's worth noting that this is the kind of thinking behind one of Hawking's popular science books. It's called Black Holes and Baby Universes. And it's still speculative, we don't know, but it's just asking the question, could it be that what started our universe, which was emerging from a Big Bang singularity, was maybe some kind of cyclic thing where in a previous cycle you had a black hole collapsing.
Yeah.
And again, there's a lot of speculation around that is sort of also to do with maybe trying to get a grip on why our universe is so big and so old, that maybe one of the things that makes our universe so big and so old is that those are good conditions for black holes to form, because black holes will typically form at the end of a star's life. Mm-hmm. And you need your universe to be big enough to have lots of stars in it and old enough for the stars to reach, the end of their life. So it almost seems to echo some of the ideas in things like, natural selection and biological systems, that things aren't like created a certain way, they just kind of evolve that way because that helps them to survive a kind of selection.
And you mentioned about things, spherical objects, when they collapse, there's nothing to stop them. This might sound silly, but why is everything spherical? Is it gravity? Is that what causes things?
Basically, yeah.
Why are all the planets and everything's spherical?
Basically, yeah. But again, it's not even that simple, because things don't often wind up spherical. They might start off spherical. If you take, like, say, the planets in our solar system, they're orbiting in a plane around the sun, so when our solar system was forming, it might initially have been a big spherical cloud of gas, but as it collapsed under its own weight, then something caused it to become like aspherical, to become like flattened in a disk. Mm-hmm. Again, we understand that too. It's tied up with some of the ideas we've discussed about the conservation of energy and momentum. But in the case of a black hole collapsing, we think, or a star collapsing into a black hole, we think that probably happens so fast that there isn't really enough time for any departure from the spherical shape. You often wind up with things being spherical just because of gravity. It's why, like, say, our moon is roughly spherical, but some of the really tiny moons of Jupiter and Saturn, they're not. They're like potato shaped because their gravity isn't strong enough to kind of smooth off the rough edges. But if a body is big enough, then under its own gravity, it will naturally tend to clump together into a spherical shape.
Oh, that's interesting. And that was sort of my next question, was about the shape of the universe, because then when I think of the universe, I see it as a sphere.
Yep.
An ever expanding sphere. Would that be correct, or is it just going to be some crazy?
No. I mean, well, put it this way: we have no reason to suppose that the universe has a different shape than that. It's something we can, in principle, try to measure. So, if you consider, like, say, a beach ball and a saddle or a Pringle, it'd be a pretty big Pringle. Those have got different geometries. So. One is like, it's called an openly curved surface, whereas the beach ball is a closed curved surface. Now, okay, that's just a label, but what does it really mean? If you try drawing a triangle on a saddle shape, on probably a bit hard to draw one on a Pringle, what you would find is that the angles of the sides of the triangle add up to less than 180 degrees, which is a bit weird, because that's one of the things they drum into you at school, that they add up to 180. That only applies on a flat surface. Similarly, on a beach ball, the angles would add up to more than 180 degrees. So this is a kind of analogy for measurements we can make in our universe, which are equivalent to that, equivalent to measuring angles on a surface, which basically tell us what the shape of our universe is. And we don't see any evidence of it being other than spherical.
My first thought on that is like flat earthers who think the earth is flat. Like, why just you could surely use some sort of geometry to just theoretically draw a big triangle.
Don't get me started on flat earthers.
Draw a big triangle and then work out that if the angles are more than 180, then it's definitely a sphere.
There are so many ways you can rule out the flat earthers' theories. I mean, a lot of them seem to emanate from people that travel a lot and post on YouTube about how the airlines are faking it when they're flying to Australia. They're having a kind of video on the window so that you're not really seeing the curvature of, you are seeing the curvature of the Earth, but it's just a video projection.
Yeah.
Right.
Well, okay, I'll give them that. I don't know. But what about when they land in Australia and notice that the sun goes that way round instead of that way round? I find it astounding. I mean, again, that takes us back to what we were saying about talking to a class of primary school children. My approach there is not to go in and say, believe me because I'm a clever scientist. It's to just get them to use their own thinking skills themselves.
Yeah.
And you might well find that some of them have even been to Australia or other things that they can draw upon from their own personal experience that clearly show that
Who worked
that
that
the
out?
Earth
Who
is...
worked that out? Who was the first person to work? Is that known? That worked out that the Earth was a sphere, not flat. Because we used to believe it was flat. I think.
Well, no, I mean, I think we're really doing our ancestors a gross injustice because
probably.
There was a... We don't know if this person really existed. It might just be a kind of a cipher for a team of people. There was a great library in Alexandria that was destroyed. I don't know exactly when. I'm not good in my dates in history, but Egyptian times. So you're talking about 3,000 years ago or so. And there was a scholar that worked there called Eratosthenes. Again, possibly not a real person, but just a kind of a label for a group of people. But the story goes that he was aware that in a certain location at midday, the sun would be directly overhead. Whereas in a nearby location, Alexandria, so I think the first location was Syene, not sure where that is, but a few hundred miles from Alexandria. Yeah. Whereas in Alexandria, the sun at midday would shine with a certain angle.
Was it not the obelisks? They built obelisks and realised that there was no shadow on this one, but there was on that one.
Exactly. And if you know the distance between the obelisks, then
right.
It's just simple high school trig to work out. So, I think it's wrong for us to say that, our ancestors all thought the Earth was flat, because some of them didn't.
Yeah.
And then the other evidence that was very strong is that when you have a lunar eclipse, which means that the Earth passes between the moon and the sun, so the Earth's shadow is cast upon the moon, you see the shadow is round, right? You see the shadow as a curve. You don't see the shadow as a line. Mm-hmm. Now, if the Earth was flat but a disc, then you could sometimes make that work. But it's only with a spherical shape that whichever direction the light's shining from, the shadow is always a curve.
And what's amazing is they've got answers for all these things, though. They've got answers to them all. Like
it's not
an answer for everything. It's like, no matter what you say, no matter what evidence you present,
doesn't mean they're right.
Did you watch the one? I think there's a Netflix special. Did you watch it? And at the very end, the guy sends the laser beam to his mate who's a few hundred meters away. And obviously, if the Earth is flat, a laser would be able to go through. I think he holds it above his head, and he's got a target, and they've measured it all. And it's this scientific experiment, and the laser misses, obviously, because the curvature of the Earth. And then he's just like, the laser must be broken. It just moves on.
Sure.
And you're like, this is crazy.
I try not to get too exasperated by all that stuff. I mean, my approach, I've also done a lot of outreach around debunking the moon landing conspiracy theories.
Right, okay.
And my goal there is not really to try and convince the people that say we never went to the moon, because, again,
So you're saying that we did or didn't land?
Well, I can't definitively say that we did, but what I can do is I can debunk the theories that are put forward by the conspiracy theorists to say that we didn't.
Right, okay. Right.
But in a way, I'm more interested anyway in equipping school children with the logical thinking skills to do that for themselves, or at least to reach their own conclusion, and not just believe it because the teacher says or because their uncle says, "Oh, we never went to the moon."
What are some of the moon landing conspiracies?
What's the strongest point for it not happening?
There's quite a lot, to be honest, so it's hard to narrow it down. But let me, maybe two, if you're giving me two. For me, the biggest two are that if you look at the video footage of that astronaut that I mentioned before, dropping the hammer and the feather, it's not just that they hit the ground at the same time because there's no air in the moon, but it's also that they actually accelerate at a different rate because the moon's gravity's different from the Earth. It's not as massive, so the gravity is about a sixth. Now, okay, that could have been manipulated. I appreciate that from the perspective of 2022, because we're all used to everything being done in CGI. But this was 1969, and it doesn't seem very likely to me that they would have gone to that level of trouble. Moreover, from Apollo 15 onwards, they had the lunar rover, and there's some wonderful shots, and again, we've done the analysis with high school kids, where you see the dust from the wheels of the lunar rover getting thrown up, and it goes in the shape we call a parabola, which is like, if I throw something across a room, like a heavy thing, it'll follow a parabolic path, a curved path. Dust wouldn't do that on Earth because dust floats. We're back to our air resistance again. So what you're seeing there is the dust following a parabolic path with a curvature that matches the 6th Earth gravity that you've got in the moon. If it was filmed in a studio, they would have had to fake all that as well.
It's hard work.
Just in the end, it just seems easier to conclude that we actually went to the moon. There's so many details like that they get right. Now, another one, the conspiracy theories, this is my second one, that they would point to the fact that you don't see stars in the sky in the lunar photos. Well, that would have been easy to fake, frankly. But the reason you don't see them is because they're not actually visible from the moon's surface. The moon's too bright. It reflects a lot of light from the sun, and therefore you wouldn't see those stars in a short exposure photograph. But again, you don't need me to believe it. What I have done frequently with primary schools is encourage them to kind of try this out and basically build a wee model with a bright light reflecting off, say, a papier-mâché or clay surface, real Blue Peter stuff, and then little LED lights that would be like the stars. And if you just take a short exposure photo, you don't see them because it's just drowned out by the light reflected. Very much related to that is the waving flag. The symbol of the flag.
That's a common one you hear about.
But again, it's because there's no air resistance. What you see the flag doing is waving because they've been twisting the flagpole back and forth.
Yeah.
And then the flag will keep on waving because there's no air resistance to slow it down. So what we did with a few high schools, because they needed better kit, but the primary schools could get involved as well, was build a little setup with like a bell jar with a flag inside, and then you evacuate all the air from the bell jar, start it flapping, and it keeps on flapping for ages.
Yeah, because there's no resistance.
So again, I'm not saying that, that definitively proves that we went to the moon, but what it's just encouraging school children to do is to think it through for themselves. And I've never really bothered trying to confront the conspiracy theorists themselves. I just feel I've got better things to do with my life.
You could have some fun with it, though.
You could. I mean, I've done lots of public talks on it where I've shown footage of one of them called Bart Sibrel, who, this is going back a number of years, more than 20 years now, but he was doorstepping the Apollo astronauts and he confronted Buzz Aldrin.
Really?
And Buzz Aldrin must have just got really fed up with him and he just punched him, cracking punch. So that usually gets a bit of a laugh, but I'm not interested in doing that with them. I think I'm much more interested in just trying to use this as a way to get people thinking critically about how to make sense of the world. And as we've been discussing, sometimes that's hard because the laws of physics don't behave in a way that aligns with our common sense. But you've just got to build the foundations, and then if people study science to high enough level, they'll realise all the reasons why even that weird stuff like space-time, is backed up by observations as well.
Do you think this is slightly unrelated, but it's been coming, I think, in my head. Do you think there's a meaning to life?
Oh, that's a great question. Well, yeah, but I'm not quite sure what it is, and I'm not sure how we would measure it scientifically, and I don't see that as my job. I mean, there's a great line in the movie Contact. I'm not sure if it's in the book. I have read the book, but it's a long, long time ago. But I watch the movie, every couple of years. It's one of my favourites. And there's a line where Matthew McConaughey's character, who's a kind of theologian, but it's not really clear, what kind. He's certainly got some very liberal views. Whereas by contrast, especially my colleagues in the US, often even things like the Big Bang and the universe being old and all that, they get challenged by sort of evangelicals in public talks. I don't get anything like that. So to try and home in on your question, Jodie Foster's character, who's the scientist protagonist in the film, is sort of debating with Matthew McConaughey effectively whether there's meaning and purpose to the universe. And McConaughey is sort of calling her out on it and saying, well, did you love your dad? And she says, yeah. And then, he says, well, prove it, you know, and I thought that was quite apt here. Where I derive meaning in life is the relationships I have with my family, with friends, with whiskey. I don't know how much that is based on objective reality or not. I mean, I suppose it could be that the reason I like this whiskey more than another one is because of the chemicals in the whiskey and so on. You could analyse that to death. I don't want to do that. I just want to enjoy the whiskey, and it's kind of my approach to understanding the universe. I find the universe fascinating. I find what we've found out about it really kind of uplifting and rewarding. But it's not a quest for meaning. If it turns out that there's no meaning to the universe, I don't think it somehow devalues what I've learned about it in all this time. I lost my father a few months ago. He was 93, so you know, a good innings. But one of the consequences of not travelling much during COVID is that I was able to spend a lot more time with him than I would otherwise have done. And you know, we had some of these conversations, I suppose. He'd had a stroke. We knew that he was, you know, on a terminal decline, but he hung in there for long enough that we could have good chats about, well, things like, you know, all the football matches he remembered seeing when he was younger and stuff like that. And we didn't get super deep and profound talking about, you know, the meaning of life and stuff, but I think he had always been aware that what I was working on was stuff that kind of touched a wee bit on that. Mm-hmm. But, you know, I think from his point of view as a parent, and I would just try and do the same, you know, with my own daughter, that all he really cared about was whether I enjoyed what I was doing, you know, and it wasn't that, oh, right, you're doing all this astrophysics to find out what the meaning of the universe is. It'd be kind of nice if we did, but it could be that there just isn't any, you know, and we're just here as a kind of random fluctuation from the Big Bang 14 billion years ago. As I say, my approach there is to respect those that seek that meaning, and we're all on different paths, and I know some people would challenge some of the things that I've discovered about the universe because it goes against their beliefs. Well, in the end, you know, if it comes down to what the science says, I'm always going to favour that, but it doesn't mean I have to trample all over their beliefs. And sometimes, you know, this is where the kind of common links that we all have, being able to enjoy a glass of whiskey together, can get you past any of that kind of stuff, you know, where people think, oh, you're a scientist, you've killed God or something like that.
Yeah. That the question definitely wasn't backed with some sort of a idea of mine or any preconception of what your answer might be. I'm just curious. You're way more educated. Yeah. So my question, there was no idea that you've killed this. You've killed the meaning of life or religion or anything like that.
It's a great question, and again, maybe I know I keep being drawn back to James Clerk Maxwell. But he was a product of his time, and he was deeply religious, but like everybody was then to some extent. I think, I mean, you know, I come from, you know, Irish Catholic descent. I mentioned before that I'm a Celtic fan. So obviously that's been a backdrop to my life. I'm kind of comfortable with it in a way that maybe some of my scientist colleagues wouldn't be so much. I'm not sure how much of it I really believe, but, you know, it's part of our culture. It's woven into our culture. If you go back to James Clerk Maxwell's time, it was much more the case that, you know, it was just part of the establishment that you believed in, you know, the traditional view of, you know, God with a white beard and a cloud sort of thing. But I think where Maxwell still resonates for me today, even if he expressed it in a very different way, was his sort of desire to understand on a really deep level how the universe works. It wasn't necessarily that it was created by somebody or something. It wasn't necessarily that it has a meaning or purpose, but he still felt that there had to be kind of rules describing how it all works. And I still think that today. I think it's just that the rules are a bit more complicated than we thought they were going to be, which is why we've not got our theory of quantum gravity yet, for example. But, you know, the quest to understand things, I don't think it takes away from the quest to understand ourselves, which I think for me is much more what religion is all about. You know?
Yeah, I think it's actually interesting, and it poses the question or as to how these early physicists and scientists reconciled theology and the belief in God and actually some of their discoveries, because they do at times they can sort of go against each other.
Again, I suppose it just depends how literal you're going to be. I mean, so Lord Kelvin was a contemporary of Maxwell's, good friend of his as well.
Is this no, he's not on the wall here.
He's upstairs.
He's
I think,
upstairs.
on the wall. Yeah.
So he was known as William Thomson. So he was professor in Glasgow University for decades and decades. So in some sense, I'm a successor of him when I was head of physics and astronomy. And then we've got another, Kelvin professor now who holds that chair. And I guess for him and for Maxwell, it was just so woven into the establishment that, that was just what you thought.
Yeah.
At the same time, a literal interpretation of the chronology of the Bible would place the age of the universe at something like 6,000 years. And Kelvin was perfectly well aware, as other scientists, people like James Hutton, who was a geologist based in Edinburgh, that the Earth was a heck of a lot older than that. So I don't really know enough about the history of these people as to whether they saw that as a problem.
Yeah.
I suspect that they probably just figured that the Bible was like stories, and that it wasn't to be taken literally as 6,000 years. But let's face it, there's still a lot of people today who do think that literally we should interpret it like that. And I mean, how they would reconcile science with the Bible, I have no idea.
How old is the universe? We're talking 13, 14 billion?
Just under 14, but 13.8 billion years.
13.8 billion years.
So again, that's our best guess, but it's a pretty accurate guess, and it's based on measuring how fast it's expanding and, and then extrapolating from that back to the very early
So that's an
universe.
interesting theory or an interesting point as to how fast it's expanding. And I always wonder when I think about the expansion of the universe. Let's say there is a point, there's a piece of rock right out there that's the furthest most piece of rock, right? So if the universe is expanding, or there must be something that's at the edge, the very edge.
There is an edge, but it's a subtle thing. That there's a horizon in the sense that because the speed of light is not infinite, we can only look so far back, because we can only look far enough back that there's been enough time for the light to reach us.
Yeah.
But there could be, and there almost certainly is, vast swathes of the universe beyond that horizon. And indeed, the universe could be infinite. I mean, we don't know. And we might never know, because we can only observe a finite part of it that there's been enough time for information to reach us from.
So in that, correct me if I'm wrong, are we saying so the universe that we are talking about could, in theory, be part of a larger
absolutely.
a larger thing, a larger universe?
We think it's very likely that there is. And again, you can have it on kind of several levels. You can have like a universe, but with just like large parts of which lie beyond our horizon. So maybe a good analogy here is just like the Earth itself. Prior to heavier than air flight, there was kind of a limit to how far anyone could travel, and then suddenly they could travel a lot further. So we knew that there was more beyond.
Yeah.
The trouble is, because nothing can travel faster than light, we'll never get beyond that horizon. But in the very early universe, we think there was a period of really rapid expansion called inflation. We know a lot about that now in another context. But cosmological inflation, we believe, happened a tiny fraction of a second after the Big Bang and greatly expanded the size of the universe that lay within our horizon. And again, it's pretty esoteric stuff. It's maybe a bit hard to describe just waving my hands. But the upshot of all of that is that beyond our current horizon, there probably is a lot more universe that's out there. But in addition, what you can also have is multiple universes.
Yeah.
So you might think, oh, well, that's just splitting hairs. But in some sense, really, they are different. You can have a big chunk of unobserved universe that still originated from the same Big Bang, but you could also have lots of Big Bangs.
Yeah.
You could have lots of episodes where a universe pops into existence. Remember, we discussed before that could possibly be as a result of the collapse of a black hole in a kind of earlier cycle. That's an idea that's been speculated
And that
about.
could happen thousands of times. millions of times, over and over and over again.
Exactly.
Over millions of years.
So there's one flavour of inflation called eternal inflation that is basically that, where these inflationary bubbles are popping up forever, and we just happen to be in one of them. And well, why should we be in this one? Well, maybe that's something to do with the fact that for us to exist, it needs to be quite big and quite old. It needs to have stars in it. It needs to have the right kind of chemicals in it.
It needs to be very specific, doesn't it, to create life? And you mentioned earlier about when Harvey asked what...
Well, at least life like us.
Life like us, for sure. And that's what... When I think about life on other planets, we talk about our galaxy and our solar system and then our galaxy. Life, I think people, when we talk about life on other planets, we think about complex multi-celled organisms that are walking around talking to each other with culture and whiskey and podcasts. But the chance of that in our galaxy is surely very small.
Well, we don't know. I mean, there could be a lot of them out there, but then you've maybe got your Fermi paradox problem. If they really are all out there as complex evolved civilizations, where are they?
The chance of single-celled organisms
much higher,
is much higher. And even in our own galaxy,
that's
there's probably
absolutely
a very good chance that there's a single-celled organism somewhere in our galaxy.
Well, lots of them would be my contention.
The chance of there being a complex multi-celled sort of...
Maybe that's lower. Agreed. There's a lot of things can go wrong. The universe could, put paid to an evolving species, an evolving civilization in a whole host of different ways.
Well, we've seen it even on planet Earth, with mammals, dinosaurs, and all
that stuff.
There's various extinction events that have happened over the last 20 or 30,000 years that have killed off.
So this is one of the things that Carl Sagan was a strong advocate about, and it was partly to draw attention to not just the ways the universe can kill us, but the way we ourselves can kill us, and the importance of trying to preserve the planet. And I mean, that message is as important today as it was back when he was first saying it in the 70s and 80s. So I honestly don't know, but my gut feeling is that the conditions that allow life like us to exist maybe are a bit fine-tuned. And one way you can resolve that apparent paradox is to say, well, we live in a multiverse. And I find it fascinating the way that concepts like that are now finding their way just into popular culture in a way that they absolutely weren't when I was much younger. I'm a big fan of sci-fi, as I mentioned. I like my Marvel movies. I like the Star Wars movies. And it's really interesting to see the way that a lot of these ideas are now more commonly accepted or talked about because they pop up in Hollywood films.
Does it make sense from a physicist's point of view?
No, some get it better than others. I mean, like Interstellar, we mentioned before, the science is speculative and beyond what we currently know, but it's plausible. The Martian is absolutely spot on in so many ways. It's a great film.
I'm a big fan of The Martian.
It's a brilliant film.
But at the same time, there's other sci-fi that just totally gets it wrong. But hey, I still enjoy it anyway. It's fun.
Yeah.
Doctor Strange in the Multiverse of Madness is not, from an astrophysics point of view, very, very good. But
I think
I enjoy it anyway.
Neil deGrasse Tyson gets into Twitter spats with people, doesn't he, over stuff like that. And I think if I remember doing something where James Cameron. He tweeted that the star constellations in Titanic in the final scene were wrong.
Right.
For what was happening then, in 1912 was it? Was Titanic sunk, and Neil deGrasse Tyson sort of worked out what constellations and what stars you would be able to see in that place at that time. And James Cameron then went back and has changed it.
Good for him. I must admit that's one of my bugbears. I mean, my wife for a number of years worked with the Scottish Opera. She's not doing that now, but she was one of their rehearsal pianists, and so we're going to the opera tonight. And over the years going to see productions, it used to always annoy me that they would have this wonderful backdrop with all the starry lights, but they didn't look like the right constellation.
It's always got Orion's belt or the Big Dipper on it, always, no matter what.
Well, to be honest, a lot of the time they didn't even have that. That would have been good, at least, if they had that, But I always used to say, well, look, I'm happy to be technical advisor if they'll have me. Little things like that, I think always happy to give Hollywood a free pass on those.
Yeah.
But I think if it's woven into the plot line, then it's good to get it right. So, and it can often work in your advantage. I mean, the fact that speed of light is finite, it means that when you're communicating with someone on Mars, there's a time delay.
Yeah.
And that can actually add to the tension of the plot.
That can add to the plot.
So like one of the series I've really enjoyed watching in lockdown is The Expanse on Amazon, and their science is really good.
Oh, is it? Right.
Absolutely spot on. And often things like that, the time delay in communications is part of the story, you know, because you're effectively cut off, you know, from what's happening in other planets and so on.
And that one of the big themes of Interstellar, you mentioned earlier, is that gravitational time dilation.
Yeah, absolutely. Yeah.
Which I think is just the most interesting concept ever. And we kind of touched on it a little bit, and I had some thoughts on it, and it's very sort of difficult for me to articulate my thoughts on it, but I'll definitely try. Now, my understanding of it is that time, and you've kind of described a little bit, time is relative to if you're standing...
The gravitational field. So it runs at a different rate depending on the strength of the gravitational field.
So it runs slower the closer you are to a large gravitational object. So if you're on Earth, and if then Harvey jumped in a rocket ship and flew 10,000 miles into the middle of nowhere, time would travel faster for Harvey than it would for me standing on planet Earth, relative to me.
Basically, yeah. And although you've also got to be careful because it will run at a different rate while you're traveling. But if you say compare the GPS satellites, which are just up there at a fixed altitude, then yes, time is running faster for them and more slowly for us down in the ground.
Perfect response, because it feeds into exactly what I'm going to say next. If you were able to plot a course through the universe that kept you either a consistent distance away from any gravitation or mass, any massive objects at all, any gravitational fields, could you not then theoretically be time traveling relative to Earth? So
yes, absolutely.
So if you plotted your way away from all the sort of clusters of mass in the universe, you could essentially travel from point A to point B very, very quickly compared to what the person on Earth is experiencing.
Well, sure. I mean, in a sense, we are all time travelers, right? Because we are traveling through time all the time. We can choose to not travel through space, but we cannot choose to not travel through time. Sorry for the double negative. You know, we have got to have time flow past us at a certain rate, but we can change the rate at which time flows past us by changing our velocity and our acceleration. And there's some very good sci-fi examples of this. So in some sense, Interstellar is the benchmark here because of the way in which their trajectory takes them in and out of strong gravitational fields. Then different amounts of time elapses for the astronauts on board compared with his daughter back home.
Yeah.
There's a very nice example that's never, I think, come close to being turned into a film. I don't know if it would really work as a film, but it's a book called The Forever War by Larry Niven. Joe Haldeman. And it's essentially an allegory of the Vietnam War. Okay. But it's set in the far future where the human race is at war with an alien species. They never actually even get to meet the alien species, and when they finally do, they realise that it was all just a horrible misunderstanding. But the point is, because all of this is conducted in spaceships that go through black hole singularities, then there's an awful lot of time dilation happens. And the interesting bit of it is that it means that the soldiers fighting at different stages in the war are often at an extreme disadvantage because they've effectively jumped forward a few hundred years with like old tech, which meanwhile the aliens have like jumped ahead. So, but equally other times it works the other way. So yeah, absolutely. I mean, that I think is the only absolutely nailed on possible way to travel forwards in time is exploiting that time dilation. Yeah. I mean, like you, Harvey, I would love us to be able to travel backwards in time as well, but we don't really know if that is allowed. It certainly isn't allowed strictly within general relativity, but travelling forwards is
no problem. And it's just about, ultimately it's about working out how to reduce that dilation so much that it almost appears instant.
Yeah, indeed. And I mean, one of the characters in that Joe Haldeman book, it's like the two protagonists, you know, as if all the battles and stuff weren't enough, it's kind of a bit of a cheesy love story as well. And they wind up like in separate timelines because the time jumps that they're experiencing through time dilation mean that, you know, they start off the same age, but they're not. And one of them winds up just doing a journey close to the speed of light back and forth for decades to try and catch up. It's kind of sweet in a way.
To age or to wait.
Well, not to age, but
not age.
It was because the other person has jumped ahead. They're still young in terms of their own timeline. But if they were to then just allow time to flow at the standard rate, then they would have died before they caught up. So didn't explain that very well, but I think
it makes sense. It definitely makes sense. That's
what
so interesting.
What do you think's the next big discovery?
Well, a field that I don't work directly in, but it's very closely related, is the search for dark matter. Dark matter, we don't know what it is, but we're pretty sure there's a lot of it there because of the effect it has on the stuff we can see. So galaxies spin faster than they should if it's just all the luminous matter causing the gravity. So the general belief is, in the cosmology community, is that there's some maybe little tiny particle that we haven't discovered yet, but there's a lot of it out there. And there's a number of my colleagues, some in Edinburgh, some other parts of the UK and all around the world, who are building detectors to try and catch some of this dark matter. And I think that would be awesome if we can do that.
And is that out in space, or are you talking about there's dark matter?
There's a mixture of possibilities. Yes, we think it's basically everywhere.
Right.
But one of the ways that we could seek to detect it is by looking at faraway stuff in the universe. And it's like measuring those triangles again. Depending on how much dark matter there is, will change the geometry of those triangles. Well, not quite, but the equivalent for astronomy of measuring how bright things are. We can basically tell how much dark matter there is by how bright things are at different distances away, and how that relates to a quantity that we call the redshift. So that's one way to try and tell that dark matter is there, but it's very indirect. The other way is to actually build a detector and try and catch a dark matter particle. We're pretty sure whatever this stuff is, that it doesn't interact with things very much. It's very weakly interacting. So the name that's given is a WIMP, a weakly interacting massive particle. And some of the detectors that have been built are just designed to have, a load of molecules or atoms sitting around waiting for a dark matter particle to collide with one of them and then see the effect.
Fairly recent. Who has discovered this?
We've been looking for this for a long time, but there's been some quite significant steps forward. Right. There's still no definitive detections, but I think we're a few hints.
There's a name that comes. I can't remember the name.
There's quite a few, to be honest. No. Well, you might well be, but I suppose it depends who the story was about. One of the leading figures in this country is actually a professor in Edinburgh called Alex Murphy. And Alex is heavily involved in a number of these experiments to try and catch dark matter particles. So I'm kind of rooting for Alex. That I think really if that discovery is made, that'll be a really big thing.
How does that relate to dark energy?
Good question. Dark matter is matter. It's just not visible. We don't quite know what it is, but it has the effect of attracting other things towards it. Whereas dark energy seems to be almost like antimatter. It seems to be pushing the universe apart even faster than it would otherwise be. We really don't know what dark energy is, but we think it might be something to do with the vacuum of empty space and the kind of quantum properties of the vacuum. So it brings us back to the point I was making before, that we've got this problem with GR, general relativity, working in many situations, quantum mechanics working in other situations, but we can't seem to bring them together. If we could, then that would probably give us very strong hints as to what dark energy was.
Is quantum mechanics, that was the work that Stephen Hawking was he leading light in that? Was he?
He was, but lots and lots of people long before him. The real birth of quantum physics goes back to around the time of Einstein himself, and the thing that Einstein actually got the Nobel Prize for was discoveries to do with quantum physics, to do with the fact that light seems to come in little packets of energy that we call photons. But the other big names around that time are people like Niels Bohr, Marie Curie, Werner Heisenberg, Erwin Schrödinger, and you might have heard of Schrödinger's cat.
Yeah.
So these were people doing stuff in the early 20th century, just trying to get to grips with the nature of matter and whether we always have to think of matter as particles or whether sometimes it can behave like a wave. And the reality weirdly seems to be that it can be either. and it kind of depends what way you're looking at it. So quantum physics is weird.
Yeah.
There's a really good popular science book called How to Teach Quantum Physics to Your Dog, which I would highly recommend. It's written by someone that had to teach this stuff at uni to like first year students, and he used to kind of rehearse what he was going to say when he was out walking his dog in the morning.
Right.
And he realised that actually it would be quite a kind of funny way to tell it, as if he was telling it to his dog. You know, and the dog asked very good questions.
Yeah.
So I've got the same base knowledge as a Labrador.
Oh man, if you're a Labrador, I must be a frog or something.
You're that squirrel you were talking about earlier that you've just thrown up a building. I always just wonder, as with the expansion of the universe, what do we know what speed we're expanding at, and relative to this, and why is light so slow? Because the universe is huge, right? And then we talk about light years, stuff being like 3 million light years away, and I'm like, what you'd think it would make sense for light to be a lot faster.
It's a good question. I mean, light by any conventional human standards travels really fast, and yet it's still the case that the universe is very, very big compared with the speed of light. So, you know, the typical time for light to cross a substantial chunk of the universe, you're talking billions of years, not even just
it's
millions.
Extremely slow.
Yeah.
Relative to the size of the universe.
One way to, I mean, I'd prefer to think of it as, but you know, I can see, yes, that's a valid way to look at it, but just that an equally valid question is to ask, well, why does the universe have to be that big, given the speed of light? Why does it have to be that big and that old? I mean, I'd mentioned that in those terms. You're right. I mean, you could say, well, instead, you know, why does light have to be so slow? Again, we don't know, and it could be that if there is a multiverse, then you've got other universes where the speed of light is different, where the universe would therefore be bigger or younger or less dense or more dense. And again, the aspects of this that link to all those other questions we've been chatting about, like, you know, life and where it comes from. Well, maybe in those universes, it just couldn't be that life like us could exist because there wouldn't be enough time for life like us to evolve.
You hear about meteors and things coming in, the end of the world and things. What do you think? What's the biggest threat to humanity?
Oh, probably ourselves, to be honest.
Right.
You know, I'm not trying to be flippant. I mean, I really don't think that. But at the same time, just a few weeks ago, NASA conducted a mission which was banging a small space probe into an asteroid. And that was in order to establish that we could actually change the asteroid's orbit. So, you know, the threat of collision from a decent-sized asteroid, it's there. It always has been. It's happened numerous times in the past. It's what wiped out the dinosaurs. We now, remarkably, stand at a point where we could actually do something about it. Now,
Did it work?
The orbit's been changed. I mean, by a tiny amount, so that's what I was just going to say. You know, if you discover a month before the asteroid's going to collide, it's too late. Right. But if you discover a year or 10 years before, then this is the kind of thing you could do. You could nudge it onto a different orbit. And I think that's a bit of a game changer. Yeah. There's still plenty of other ways that the universe...
tonight.
Absolutely. This will help you sleep better. Even the asteroid that's going to hit Earth is already on its trajectory. Now. It's already on the way. So it's like, it's not like it's just going to hit us at some point. It's already coming for us. So that's going to really help you get down nice and early.
It isn't actually something I lose sleep over.
But we get near misses all the time, right?
We do.
By near misses, I mean, you're talking 10,000, 15,000 miles and stuff.
Anything inside the orbit of the moon is a bit too close for comfort, and the moon's about 380,000 kilometres from the Earth. So, you know, that's already quite far by human standards.
You can go online and see a log somewhere. You see, and there's been like 8 this year, and you look at it, you're like, oh my goodness.
Well, I mean, ironically, I was on BBC Radio Scotland when there was an event, an asteroid that, it was only very small, so I shouldn't call it an asteroid, it was a meteorite, which became a meteor. Because a meteorite is the thing that gets to the ground. You know, a meteor is just the trail in the sky. You know, this one almost certainly did get to the ground. I'm not sure if they ever found the remnant, but it was in a place in Siberia called Chelyabinsk, and you might have heard about this one back in 2013, if memory serves. And it was seen by a lot of the cameras they have in cars, you know, like I think in Russia apparently a lot of people have this, maybe in other countries too, dash cams, so that if they're in a collision they can prove it wasn't their fault, or try to. So this was really spectacular. You could see it streaking across the sky.
I have seen the video, yeah.
Did you see the one in Scotland though recently as well?
I didn't, but I have some friends that did. Yeah.
Yeah, I was driving home from the gym with Ben, and we were like driving just down the road, going home, and it was like this huge green flash across the sky.
Yep.
It was
very
insane.
impressive.
And then you jump on Twitter, and it's like it's all over Twitter. There's loads of people managed to capture it on video, and it's just and it must have been massive.
Yeah. So
that was close, small but close.
See that one in Chelyabinsk. So that was seen. We didn't get any warning, and there was actually one, I think either the day before or the day after. You know, so it would have been easy to go on BBC Scotland and say, "Oh, don't worry, this is a kind of once in a lifetime thing," but it maybe isn't. You know, again, they were both small. But that Chelyabinsk one, I mean, it did a fair amount of damage, you know. So
who's looking? Who's like, what's happening? Who's on top of this?
There are networks of telescopes that are looking for the bigger ones and trying to essentially map the orbits. I said I'm a big sci-fi fan. Another novel that I have always hoped would be turned into a film, and I believe it's going to be, and it's the director of Dune, Denis Villeneuve, and Blade Runner is going to have a stab at it.
He's great.
So the movie is Rendezvous with Rama, and it's set in the 24th century, and the prelude to the novel is by Arthur C. Clarke, the guy who wrote 2001: A Space Odyssey. The prelude to the novel is imagining a fairly disastrous asteroid collision, not enough to kind of wipe everything out, but to, you know, kill hundreds of thousands of people and trillions of pounds of damage in Northern Europe. So I think that was supposed to happen in like 2060 or something. And in the context of the novel, what happens is that they set up a project called Space Guard to just like monitor the stuff that's out there and make sure that it would never happen again, that we would get no warning. And effectively something like that has happened. Now, fortunately, it didn't take a collision to trigger it, but there are projects that are doing that kind of thing and are monitoring kind of everything above a few kilometres in size. Now, even the smaller ones could do quite a lot of damage, but they wouldn't like wipe out all life on Earth. So I think the sort of extinction level events are unlikely. Don't quote me on that.
They're pretty big though, right? They would see that coming, I think, nowadays.
It's all a case of how long you would see it in advance. If you could see it coming, we now have the capability to do something about it.
No, we know when it's coming now.
Yeah.
For 10 years, we just know it's
Martin's saving us.
I mean, did you see the movie Don't Look Up?
Yeah.
You know, again, I think it is, and I mean, how realistic was that? Well, okay, it was designed to be a bit kind of like heightened melodrama. It was very funny. I like to think it wouldn't be quite that bad, that if we really knew it was coming in 10 years, that, you know, the Earth would mobilise to do something about it rather than just pretend it wasn't a problem.
The films that are tongue-in-cheek, I suppose you're not too offended by the ones that are like supposed to be kind of funny and dramatic. The ones that take themselves seriously, they're the ones that probably bother the astrophysicists.
Well, it's funny the way that they come about. I mean, like, maybe this is what you were thinking of. Armageddon was very much like the former. I mean, it was tongue-in-cheek. I thought it was a great laugh.
It's a great film.
Very funny. The one that was a bit more serious, or thought it was a bit more serious, was Deep Impact.
Yeah.
And I mean, aspects of that were a bit unrealistic as well. But hey, you know, if it helps more people to be aware of the problem, then it's a good thing.
And it brings people into that sphere as well of understanding. Like you said before, you've never at a time on Earth have we ever had such engagement probably with this type of stuff. And,
nope.
And I remember actually in our very first conversations, when Harvey and I spoke about sort of bringing on podcast guests, I was like, let's find somebody to talk about space. Let's go find somebody then. And then you and I sort of had some early conversations, and I was like, listen, I'm just interested in this stuff. I've got a childlike curiosity. We think we both do.
Yeah.
I think a lot of people do, as to what's out there and what's happening and how all this stuff works. And it's really interesting. But media and sci-fi and these amazing films like you're talking about, Interstellar and all these things that are coming out, that really spark the imagination. And this stuff's extremely popular now.
Yeah.
So it's great to see, and hopefully it sort of it lends itself to more great scientists who get inspired when they're young children. And
well, I certainly hope so, but I think on a more broad level, not everyone's going to be a scientist, but science affects our lives so much, and it affects the decisions that we make. You know, look at the decisions around vaccination, for the pandemic, you want people to be making those decisions from an informed standpoint. And just helping to hone their critical thinking skills is what it's all about.
Yeah.
Who's your hero?
Yeah, good question. I mean, in terms of history, it probably got to be Albert Einstein, really. I mean, I don't know that much about Einstein as a person, but in terms of his science, absolutely outstanding. Someone that I know a bit more about as a person, we've also talked about, was Carl Sagan. And again, I think what in a way makes him a bit more heroic-like is it's not just that he was a scientist, but he took very seriously the importance of communicating science to a general audience, which is what I try to do as well. So, yeah, so there you go.
And his fourth dimension stuff I found so interesting, and like that was about
sure
there being other life forms that just live on a different plane to us, so we have no possible way of understanding them. Is that have I got that right?
Yeah, absolutely. I mean, again, was just trying to get us to think out of the box in those terms.
There's a video and you can get it on YouTube, and it's him sitting at a table, and he's got a sort of 2D sort of room, and he's got a little guy in a room, and he's talking about how if I dropped a ball from the height,
if you had no perception of that third dimension, you would just have no idea what was going on.
Exactly. As soon as the ball hits the two-dimensional part, then it's just it's just a
it
disc.
just appears.
It's just a disc in a room that's just appeared out of nowhere.
Absolutely.
And that could be the case for a fourth dimension. It's just like I was watching it being like, oh my god, this is crazy.
I should say, of course, I'm a big fan of Kyogo Furuhashi as well. So if we can broaden the definition of hero sufficiently.
Head lasted or something I was expecting.
Yeah, absolutely.
Great. Yeah. Martin, where can people find you? Where can people find what we're doing here at the James Clerk Maxwell Foundation? Just to sign off.
So there's a James Clerk Maxwell Foundation website. There's also a LIGO.org website. So I'll make sure you've got links to those. The website for the James Clerk Maxwell Foundation talks a lot about his life, talks about the room here and the townhouse here. And also, for example, explains how you can come visit. We are available to host guided tours. And I mentioned, I think, near the beginning of our chat, that in 2031 it will be his bicentenary of his birth. So we're very keen to build up awareness of him and access to 14 Indus Street here in Edinburgh, so that people can find out a bit more about Scotland's Einstein.
Fantastic. Yeah, we came along to one of the open days. It was really busy. There was lots of people here to guide you through the rooms and do little experiments and talk about what Maxwell had done. So it was great. We enjoyed it. And,
I'd recommend anybody checking it out.
It was brilliant. Yeah, absolutely.
Good stuff.
Are you on any social media?
Yes, I am. Although to be honest, I don't post that often. I run the LIGO social media, so that's at LIGO, and that's, we've got about 110,000 followers, which of course went through the roof when we made the first discovery, and then it also went through the roof when we won the Nobel Prize, but it's kind of saturated a bit, so we're always keen to get more followers.
Well, it'll go through the roof after this goes
I very much hope so.
So we'll see what happens.
My own personal Twitter is Martin_Astro, but yeah, the LIGO one is mainly where you'll find out more about what it's all about.
Great. We'll point the viewers and listeners onto those sites.
Good
Make
stuff.
sure you get some engagement on them as well.
Excellent.
Thanks very much.
You're welcome.
Thank you very much. It was absolutely fantastic.
Real pleasure.
Absolutely.
Thank you.
Thanks, Mark.